James Webb didn't just spot distant galaxies. It may have caught the universe lying. The numbers break exactly where our best model swears they should be unbreakable, like a marathon where 100,000 runners start at the finish line and almost none survive the course. So if we're at mile 5, surrounded by life and light, what terrifying filter is still ahead? And what does it mean about space, gravity, and whether any civilization ever makes it through? The most unsettling discoveries are not monsters in the dark. They are measurements that refuse to behave. When the sky becomes a lab bench, even a small discrepancy can threaten everything we think we know. For a century, cosmology has felt like a tightening circle of certainty. Better telescopes, cleaner data, sharper predictions. Yet the newest instruments do not merely extend our vision. They interrogate our assumptions, and they do it without mercy. James Webb was built to read the universe's earliest light in infrared, to watch structure assemble from faint beginnings. Instead, it has begun to illuminate an uncomfortable possibility, one that does not require science fiction, only arithmetic. Because our best model is not a story, it is a machine. Feed it the relic glow of the early universe, and it outputs a cosmos with specific ages, growth rates, and expectations for what should exist when. Feed it today's distances and motions, and it should agree. When it doesn't, the error is not decorative, it is diagnostic. In this film, we follow a chain of tensions that look separate at first glance, but may be symptoms of a single misidentification. Are we mistaking a local rule for a universal law, treating an effective approximation as a final description? We will start where optimism feels most justified, among the swelling census of worlds that seem capable of hosting life. Then we will push outward into the deep fields, where galaxies appear with a confidence and speed that challenge the old timetable, and where every proposed fix demands a payment elsewhere. From there, we confront a universe that can't agree with itself about how fast it is expanding. Two rulers, both precise, both tested, both stubborn, each insisting the other must be wrong, and neither yielding easily. And if expansion is not merely mismeasured, but truly changing character, the consequences ripple forward and backward through cosmic history. A constant that may not be constant would rewrite the bookkeeping for ages, distances, and the fate of everything bound by gravity. Then the mood shifts from discrepancy to claustrophobia. The parameters that permit chemistry, stars, and stable complexity do not simply work. They seem to click into place like many locks on a single door, each one narrow enough to feel accidental. Finally, we arrive at the strangest ledger in physics, where information appears to live on surfaces and horizons, not in volumes. Black holes force the issue. Thermodynamics refuses to be negotiated, and the universe must keep its accounts somewhere. At the edge of that argument waits a radical possibility. Gravity and space may not be fundamental ingredients at all, but emergent behavior, like temperature arising from invisible motion. If so, the cracks in our cosmology are not embarrassing outliers. They are the first hints of the deeper architecture. This is an exploratory journey, and the camera will treat data like terrain. Maps, error bars, spectra, and faint photons turned into claims. We will move from crowded star fields to silent equations, from brilliant infrared arcs to austere boundary diagrams, always asking the same thing. What kind of universe produces answers that almost fit until suddenly they don't? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we trace how early galaxies, expansion tensions, and dark energy drift could point toward a boundary-based reality. And along the way, we confront what a deeper physics would imply for survival, silence, and the distance between starting and finishing. Imagine a marathon that starts at the finish line, with the clock already running and the banner already behind you. 100,000 runners surge forward, and the course looks wide and forgiving under clean morning light. At mile 5, the pack is still dense, and the noise feels like safety, like proof that the route is fair. But this race is designed so almost nobody reaches the real finish, because the course is not only long, it is shaped to thin the field abruptly, after the early miles have trained you to relax. A crowded mile 5 is not comfort. It is evidence that the hardest miles are still ahead, hidden beyond the first gentle turns. The air is full of footsteps, breathing, and the soft slap of shoes on asphalt. You can't see the decisive hills yet, because the crowd blocks the horizon. You can't feel the attrition yet, because the weakest trajectories have not been tested. In this story, a filter is a bottleneck that breaks most trajectories, and it does so without drama at the start. It is not a single disaster, but a narrowing of possibilities that becomes unavoidable once you reach it. Many paths begin, few paths survive, and the survivors look ordinary until the course turns. The filter can be a threshold of chemistry, of energy, of coordination, or of time. It is whatever turns a broad field of beginnings into a thin line of endings. If you are still surrounded by runners early on, you have learned almost nothing about who endures. You have only learned that elimination has not started yet, or that it has not become visible. Early success is cheap in a race where the price is paid later. The most misleading moment is the one that feels most normal. That is the emotional trap of a crowded race, and it works because our brains are tuned for local cues. We confuse company with progress and motion with direction, because in ordinary life, crowds often mean safety. We see many bodies moving and assume the course is survivable. We forget that the course can be survivable for a while, then suddenly not. The warning is not the emptiness behind you. The warning is the density beside you, because density means the decisive sorting has not happened. Astrobiology has its own crowded mile 5, and it begins with a deceptively simple multiplication. The Drake equation asks how many civilizations might exist by multiplying uncertain factors, each one a doorway that could be wide or almost closed. How many stars form? How many have planets? How many planets are habitable? How often life begins? How often intelligence appears? How often technology lasts? Each term is a guess, but the structure teaches a lesson about compounding uncertainty. If any term is a near zero, the galaxy can be quiet even with many worlds. The Great Filter is the name we give to that near zero, the step that almost nobody passes. It could be behind us, meaning we are rare because life is rare, or because complex life is rare. It could be ahead of us, meaning we are early because survival is rare, or because longevity is rare. The difference is not academic, because it changes what we should fear and what we should celebrate. One version is a miracle in our past. The other version is a cliff in our future. Now return to the race. Suppose you learn there are more runners than you expected, and the starting field is not 10,000, but 100,000. That does not make the finish more likely for you, because the finish is defined by the bottleneck. It makes the existence of a decisive narrowing more likely somewhere on the route, because the silence at the end becomes harder to explain. More runners still moving at mile 5 increases the odds that the filter is later, not earlier. The crowd is not reassurance. The crowd is probability shifting forward. James Webb Space Telescope did not set out to study the Great Filter, and it was never marketed as an existential instrument. Webb was built to look back, toward first light and the first galaxies, where the universe was young and hot. Its mission was to measure the early universe with infrared eyes, past dust and into deep time, because cosmic expansion stretches visible light into infrared. It was designed to refine our story of origins, not to threaten our story of progress. Yet the earliest images carried a different kind of message. They hinted that the universe may not behave where our models are most confident. Visually, Webb's deep fields are almost unsettling in their calm. A black canvas fills with pinpricks, then smears, then tiny islands of light, each one a galaxy seen as it was billions of years ago. Gravitational lensing bends some of those islands into arcs, as if space-time itself is a magnifying glass. The photons are ancient, but they arrive with modern precision. When we stare at them, we are not only seeing distant objects, we are testing the scaffolding of the story we tell about everything. At the same time, Webb exists inside a broader survey machine that has been accelerating for decades. Kepler watched for tiny dips in starlight as planets transited their stars, turning exoplanets from speculation into census. TESS widened that search to nearer, brighter stars, where follow-up is easier and atmospheres can be probed. Radial velocity searches measure the wobble of a star under a planet's gravity, translating motion into mass. Direct imaging attempts fight glare to isolate faint companions, and atmospheric spectroscopy looks for molecular fingerprints in filtered starlight. All of these methods push one direction. They keep increasing the count of plausible habitats, and they keep turning planets into a statistical expectation rather than a rare exception. Even the definition of habitable has become more technical and more cautious, because it depends on stellar activity, atmospheric retention, and long-term climate stability. A temperate orbit is not a guarantee of oceans, and an ocean is not a guarantee of biology. Still, every new temperate world around a common star feels like another runner still in the race. Every improved estimate of Earth-like frequency thickens the pack at mile 5. That is why more habitable worlds can be unsettling, even though they look like good news on a headline. Emotionally, we want abundance to mean companionship and safety, as if the universe is a crowded city. Statistically, abundance can mean the opposite, because it sharpens the paradox of silence. If the universe is full of starting lines, then the absence of visible neighbors becomes harder to explain without a brutal filter. If life-friendly real estate is common, then the quiet finish line suggests that something later is lethal. The crowded race makes the silence more suspicious. This documentary begins with that discomfort and refuses to look away. Webb was built to reveal the past, but its early results may function as a warning about the future, in the same indirect way fossils warn us. Not because Webb found aliens, or found a doomsday signal, or detected a cosmic message. Because Webb may be showing that our confidence rests on local descriptions mistaken for global truths. When our best model strains at its strongest points, our extrapolations about everything else become fragile. Cosmology has its own mile 5 problem, and it is built into the way we do science at scale. We live in one region, at one time, with one set of measurements made from one small planet. We build a model that fits what we can see, then extend it far beyond what we can test. We call that extension understanding, because it is mathematically consistent and historically successful. But consistency is not the same as completeness, and success in one regime can hide failure in another. A theory can run smoothly early in the race and still fail when the course changes. The standard cosmological model, Lambda CDM, is our crowded pack. It explains the cosmic microwave background, the growth of large-scale structure, and the expansion history with remarkable economy. It gives us dark matter to seed structure and dark energy, lambda, to accelerate expansion. It offers a timeline from hot beginnings to cold futures. and it matches a wide range of observations with a small set of parameters. It is the model we trust most when we talk about the universe as a whole. It is also the model Webb was expected to confirm with sharper data, and that expectation is now part of the tension. Webb's first deep fields showed galaxies that looked too massive, too bright, too early, as if assembly happened on a schedule we did not authorize. Some of those initial claims were later adjusted, because photometric redshifts can be deceptive and dust can mimic distance. Yet the pattern remained provocative, and the question did not go away. Either the early universe built structure faster than we thought, or our interpretations are missing something basic about stars, feedback, or even gravity. The discomfort is not that one dataset is messy. The discomfort is that the mess appears near the foundations. Mile 5 feels crowded, but the route markers start to wobble. The numbers still fit in spreadsheets, and the plots still look smooth, but the story underneath feels less settled. When galaxies appear mature too soon, we are forced to ask what too soon even means in a universe whose clock is inferred. Are we misreading the light, misjudging the masses, or miscalibrating the cosmic timeline itself? And if the timeline is less secure than we assumed, what else have we built on it? If our cosmological model is less stable than we assumed, then our narrative of progress is less stable too, because we borrow confidence from cosmic order. We tell ourselves that intelligence is a natural outcome of time and complexity, as if evolution is a conveyor belt. We tell ourselves that technology is a one-way climb, and that survival is mostly a matter of avoiding obvious mistakes. But if the universe is full of habitable starts and still quiet at the finish, then survival may be the rare variable. And if our physics is less settled than we believed, then our forecasts about long-term survival are built on sand. The central question is simple to state and hard to live with. If Webb is revealing that our best model strains where it was most confident, what does that imply about space, gravity, and the odds that civilizations survive the filter? The question connects the very large to the very intimate, because it turns cosmology into a mirror. It links early galaxies to late civilizations, and cosmic history to human timelines. It asks whether our sense of being on track is based on evidence, or on habit, or on the comfort of familiar equations. This chapter is the promise of the path we will take, and it is a promise with a particular shape. We will follow a spiral that starts with Webb's impossible galaxies and tightens into deeper problems, because each answer creates a sharper question. We will move from early structure to the Hubble tension, where the universe expands at two incompatible rates depending on how you measure it. We will move from that tension to hints that dark energy may drift, weakening the simplest explanation for acceleration. We will move from drifting parameters to fine-tuning, where the constants look balanced on a knife edge. We will move from fine-tuning to radical ideas about information, holography, and emergent space. Each step will test the same recurring motif, and it will test it under pressure. Local descriptions are not automatically global truths, even when they feel universal in our textbooks. A model that works here and now can fail elsewhere and elsewhen, and the failure can be subtle at first. Extrapolation is powerful, but it can become a kind of faith when the data runs out. When we mistake a fitted curve for a law, we stop noticing where the evidence ends. When we mistake a successful era for a permanent trend, we stop asking what the course demands later. That motif also returns us to the great filter, because filters are not only about aliens. The filter is a general statement about trajectories through complex space, where most routes terminate and only a few continue. Most paths end quietly, not with fireworks, because complexity is fragile and coordination is hard. The survivors are the ones we can observe, and that creates a bias that feels like normality. That observation bias can make survival look ordinary, even when it is rare. A civilization at mile 5 will always feel like it is making progress, because it measures itself against its own past. It has no access to the statistics of the dead, and it rarely recognizes the thresholds it has not reached. It can mistake early acceleration for long-term stability, because early acceleration is what growth looks like. It can also mistake a crowded present for a crowded universe, because it has not yet learned what emptiness means. So the comfort of a crowded race becomes a warning in two directions, and both warnings sharpen as our instruments improve. In the sky, more habitable worlds increase the pressure to explain cosmic silence, because the starting line looks common. In physics, more precise measurements increase the pressure to explain why our best model strains, because the deviations become harder to dismiss. In both cases, the unsettling possibility is the same. We are early on a route that looks easy, because the difficult part has not begun. Webb is not a villain and not a prophet. It is an instrument that collects photons and forces us to update our stories, even when the updates feel like losses. But stories matter, because they guide what we build and what we ignore, and they shape what risks we consider tolerable. If the universe is stranger than our model, then the future may be stranger than our expectations. If the filter is ahead, then our era of crowded optimism may be the most dangerous time to feel safe. We start at mile 5, surrounded by runners, with the finish line still invisible beyond the curve. The pack is loud, the pace is steady, and the course feels familiar, like a city route you could run half asleep. Then the signs begin to contradict each other, and the map stops matching the ground. In the next chapter, we follow Webb's earliest surprises into the first crack in the standard story. We ask why the early universe seems too mature, too soon, and what that implies about everything that comes after. Now return to the race. Mile 5 is still crowded, but the timing chips start reporting impossible splits, and the pace that once felt steady suddenly feels unreal. On screen, the pack compresses into a moving wall of shoulders and elbows, while the clock in the corner keeps flashing numbers that do not belong. The same sensation hits astronomy when a trusted pipeline returns results that are internally consistent, yet wildly surprising. Webb's first deep fields were meant to be calibration and celebration, the kind of early mission proof that engineers and astronomers can share. They became a stress test for the early universe, because the sky answered faster than our expectations could. A deep field is not a single picture of the past, and it is not one exposure that simply reaches farther. It is a deliberate accumulation of time, a stack of many images aligned to sub-pixel precision, where faint infrared photons slowly rise above detector noise. In practice, the telescope stares at one patch of sky for hours or days, and the data are combined with careful weighting. Cosmic rays are rejected, hot pixels are mapped, background gradients are modeled, and the final mosaic becomes a census rather than a snapshot. Visually, the deep field looks like velvet sprinkled with embers. And then, after your eyes adjust, those embers turn into tiny galaxies. Some are sharp points, some are smudges, and some are stretched into arcs that hint at hidden mass between us and them. Webb measures flux in infrared bands, then maps that flux to colors across filters, and those colors become the first clue to distance. The detector is counting photons, but the story we want is physical. How far, how old, how massive, how fast? Flux is simply received energy per unit area, and it is indifferent to why a galaxy is bright. A nearby dim object and a distant luminous one can deliver the same flux, so astronomy must add a second ingredient, wavelength, to break the ambiguity. Distance in cosmology is time, because expansion stretches wavelengths as light travels, and that stretching is measurable. Higher redshift means earlier cosmic history, not because light remembers, but because it has been in transit longer through an expanding metric. The concept sounds poetic, yet it is geometric, and it is encoded in the scale factor of the universe. As space expands, a photon's wavelength is stretched with it, so the spectrum we observe is a shifted version of what was emitted. In many early Webb results, redshift came from photometry, not spectroscopy, because photometry can go deeper for the same observing time. Photometry is fast, deep, and vulnerable to degeneracy, especially when the signal is faint and the priors do heavy lifting. A photometric redshift is an inference from broadband colors, anchored by expected spectral breaks, and it is often the only practical option for the dimmest sources. It works because galaxies are not featureless. Their spectra contain abrupt changes that filters can sense. One of those changes is the Lyman break, where hydrogen absorbs photons shortward of 121.6 nanometers in the rest frame. At high redshift, that break is shifted into the near-infrared, and a galaxy can drop out of bluer filters. A dropout is a powerful signature, but it is not a fingerprint, because other physics can also remove blue light. Dust can redden a spectrum, old stars can reduce ultraviolet output, and strong emission lines can distort broadband colors. Spectroscopy is slower and brighter limited, but it pins redshift by resolving lines and breaks directly, rather than guessing from integrated colors. It is the court of appeal because it replaces inference with identification. When Webb takes a spectrum, it spreads the light into a rainbow, and the rainbow becomes a barcode of physics. Emission lines from ionized gas, absorption features from stellar atmospheres, and continuum breaks can all anchor a distance with far less ambiguity. Early universe observations are uniquely model-sensitive because every conversion depends on a cosmology, and the chain is long. Flux becomes luminosity through distance, luminosity becomes mass through stellar models, and mass becomes halo mass through assumptions about baryons. Even the distance is not a simple ruler, because cosmological distance has multiple definitions that diverge at high redshift. Luminosity distance, angular diameter distance, and co-moving distance are related, yet each enters a different part of the inference. The first shock was not one galaxy, and it was not one flamboyant outlier that could be dismissed as a fluke. It was a cluster of candidates that looked massive and bright at redshifts where they should be scarce, appearing again and again across independent fields. On the deep field image, they are tiny, almost modest, but the labels beside them are loud. A redshift of 10, 12, even 15, numbers that translate into an era when the universe was still learning how to make galaxies. Some appeared to carry stellar masses like modern galaxies, only a few 100 million years after the Big Bang, and that is a hard schedule. In LCDM, structure formation is efficient, yet it is not infinitely fast, and the early clock is unforgiving. Should not exist does not mean impossible in principle, and it does not mean the laws of physics have been violated. It means improbable, given the standard growth of structure and baryonic physics, where multiple bottlenecks must all be bypassed at once. LCDM starts with tiny density fluctuations measured in the cosmic microwave background, the afterglow of recombination at about 380,000 years. Those fluctuations are only one part in 100,000, yet gravity amplifies them inside dark matter halos over time. The microwave background is not just a picture, it is a statistical blueprint, and its power spectrum sets the initial conditions. If the blueprint is right, then the abundance of early halos is constrained, and the room for surprises is limited. Halos merge hierarchically, small first, then large, in a process that resembles financial compounding more than sudden creation. The earliest era should be dominated by low-mass halos and bursty, inefficient star formation, because shallow wells lose gas easily. To make a massive galaxy early, you need a massive halo early, and those halos live in the rare high sigma peaks of the density field. To make it bright, you need rapid star formation and many massive stars, which burn hot and blue and die quickly. To make it look mature, you need metals, dust, and sometimes ordered morphology, and those require time and cycling. Metals are forged in stellar cores and supernovae. Dust condenses in ejecta and winds, and ordered structure competes with turbulence and mergers. The model allows rare peaks, but the statistics are tight, and the tail is not a playground. If too many rare peaks appear, the tail of the distribution is wrong, or the mapping from light to mass is biased in the same direction. This is where the tension begins to feel systematic, and that is why it matters. Each object can be argued with, but the ensemble pushes on the same weak points, like repeated stress fractures in the same beam. Start with the timeline, because time is the currency of too early. At redshift 10, the universe is under 500 million years old, and at redshift 15, it is closer to 200 million, barely enough time for several stellar generations. Those ages are not guessed. They come from integrating the expansion history implied by cosmological parameters. Change the parameters, and the ages shift, which is why the argument is never only about galaxies, but also about the cosmic clock. In that window, gas must fall into halos, cool, fragment, form stars, enrich itself, and survive feedback, and every step has a bottleneck. The early universe is dense, which helps, yet it is also pristine, which limits cooling pathways. Cooling depends on density, temperature, and available coolants, and cooling is what allows gravity to win over pressure. Primordial gas is mostly hydrogen and helium, with limited ways to radiate energy, so it can remain too warm to collapse efficiently. Molecular hydrogen can provide a cooling channel, but it is fragile, and ultraviolet radiation can dissociate it. The first stars can form with molecular hydrogen cooling, yet their radiation fields can sterilize nearby regions, delaying further collapse. Feedback is violent in shallow potential wells, and the first supernovae are not gentle. Radiation pressure, stellar winds, and explosions can blow gas out of small halos, turning star formation into a sputtering cycle rather than a smooth ramp. Star formation efficiency is not a free dial that can be turned without consequences, because it couples to many observables. If it is too high early, it changes rionization, background light, and later galaxy properties, leaving signatures in multiple datasets. Rionization is the era when ultraviolet photons from early sources ionized intergalactic hydrogen, and it is constrained by quasar spectra and the microwave background. If galaxies form stars too aggressively too soon, rionization would complete earlier than observed. Metallicity is a clock, because heavy elements come from stellar evolution, and they accumulate only after stars live and die. High metallicity early implies multiple rapid generations of stars, which implies both time and sustained gas retention. Dust is another clock and another complication, because it can both hide star formation and re-radiate energy into the infrared. Dust changes observed colors, it reshapes spectral slopes, and it can trick photometric redshift codes into choosing the wrong solution. Morphology is a third clue, but it is the most interpretive, because images are filtered through resolution and surface brightness limits. A compact, smooth profile can mean a mature system, or it can mean clumpy light blurred by distance and instrument response. Webb's infrared sensitivity makes it excellent at seeing rest frame optical light from high redshift galaxies, and that matters for mass estimates. Rest frame optical traces, longer-lived stars better than ultraviolet, so it is often treated as a proxy for accumulated stellar mass. That strength is also a trap, because the interpretation depends on placing the filters at the correct rest frame wavelengths. If you misestimate redshift, you misplace the rest frame wavelength, and the inferred stellar population can change sharply, even discontinuously. A galaxy that looks like it has a Balmer break from older stars might instead be a younger system with strong emission lines. The same set of broadband points can be fit by very different histories, and the differences are not cosmetic, they change the mass by factors. So the community runs the correction gauntlet, because the first duty is to test the measurement before rewriting the model. Each correction can rescue LCDM locally, but it often creates pressure somewhere else, which is how you learn where the real constraints live. First is photometric redshift degeneracy, the classic ambiguity that returns whenever spectra are missing. A high redshift Lyman break can mimic a lower redshift dusty spectrum in broad filters, and the overlap grows when uncertainties widen. A galaxy at redshift 2 with heavy dust can look like a galaxy at redshift 10 with little dust, because both can be faint in blue bands. The colors can overlap when signal is faint, and when a single band carries a disproportionate fraction of the detection. The deep field visuals make this concrete, because some sources are barely more than a few pixels above background. When you're fitting a model to a handful of points with error bars, the best fit can be a negotiation rather than a verdict. If many candidates are actually lower redshift interlopers, the crisis softens and the mass budget relaxes. But then you must explain why the selection keeps finding lookalikes and why the inferred number density still trends high in multiple analyses. Second is contamination by emission lines, which can be dramatic in young, star-forming galaxies. Strong nebula lines like H-alpha, O30, and H-beta can boost flux in one band, faking a continuum break and biasing redshift upward. In broadband photometry, a single boosted filter can pull the fit toward a higher redshift solution, especially if neighboring filters are non-detections. The galaxy is not lying. The model is being asked to infer a spectrum from too few samples. If line contamination is common, photometric redshifts scatter high, and the early universe appears more crowded than it is. But then spectroscopy should reveal a pattern of misidentified lines, and the statistics of confirmed redshifts should shift downward. Third is gravitational lensing, the universe's own optical system, where mass bends light and changes apparent brightness. Foreground clusters and galaxies can magnify background galaxies, making them appear brighter and therefore more massive if magnification is ignored. In the deep fields, lensing sometimes announces itself with arcs and stretched shapes, but it can also be subtle. A modest magnification can still matter, because mass estimates scale with luminosity, and luminosity scales directly with magnification. Lensing can explain extreme brightness without extreme intrinsic mass, which is why it is always on the checklist. But lensing requires alignment, and the probability distribution is constrained by the abundance of foreground structure and the geometry of the line of sight. If lensing is invoked too often, the sky becomes an unlikely hall of mirrors, and the fix starts to feel like special pleading. The visual metaphor is tempting, yet the math is strict, and the distribution of lensing events is measurable. Fourth is the initial mass function, the IMF, which describes how many stars form at each mass. If early stars were more top-heavy, galaxies would be brighter per unit mass, because massive stars dominate luminosity while contributing less long-lived mass. A top-heavy IMF reduces inferred stellar mass for a given luminosity, and it can make a young galaxy look deceptively heavy. It also changes supernova rates, metal production, and reionization histories, so it can't be adjusted in isolation. If you change the IMF to save early masses, you must recheck the entire cosmic budget of metals and ionizing photons. The accounting becomes global, and that global accounting is exactly where LCDM has accumulated decades of cross-checks. Fifth is stellar population synthesis, the translation layer between starlight and physical parameters. Mass estimates depend on templates for how stellar populations age, redden, and emit across wavelengths, including phases of stellar evolution that are hard to model. Different pipelines choose different priors for star formation histories, dust attenuation laws, and metallicity, and those choices matter more at high redshift. The same flux can yield different masses because the model can trade age against dust or metallicity against star formation rate. This is not a flaw in science. It is the normal consequence of inference under uncertainty, where models translate light into quantities we cannot measure directly. The question is not whether models differ, but whether the anomaly survives across reasonable differences. But the early universe is where those translations are most fragile, because we have fewer anchors, we have fewer spectra, fewer resolved morphologies, and stronger selection effects, and every missing constraint widens the corridor of plausible solutions. That is why extraordinary claims are tested in layers, and why the process can look repetitive from the outside. Teams rerun photometry, redo background subtraction, and compare independent reduction pipelines, because subtle choices can shift faint fluxes. They cross-check with alternative codes, alternative priors, and simulated galaxies, and they ask whether the anomaly survives reasonable choices. They also test completeness, because the number of detected objects depends on detection thresholds and deblending decisions. Then they go to spectroscopy, because at some point you need a hard anchor. A single line can settle a redshift, but it can also mislead if the line identification is wrong, so careful spectroscopy looks for corroboration. Robust spectroscopy looks for multiple features, consistent line ratios, and continuum breaks, and it checks whether the features agree with a single redshift solution. It turns a candidate into a confirmed high redshift object, or it returns it to the crowded middle distances. As spectra arrived, some early impossible galaxies moved to lower redshift, and the universe breathed out. Some masses dropped, some ages shrank, and some headlines quietly dissolved. As the more ordinary explanation reclaimed territory, that revision is part of the story, not an embarrassment, because it shows the system correcting itself. It also shows how hard the measurement is, because the difference between redshift 10 and redshift 3 can be one ambiguous break. Historically, this pattern is familiar, because astronomy has been fooled by distance before, and it has learned to be skeptical. The history of high redshift claims is full of early candidates that later moved, as instruments improved and spectra replaced colors. Yet the pattern did not vanish, and that is the unsettling part. Even after revisions, there remained galaxies that were still too luminous, too massive, or too numerous for comfort, and they appeared in enough datasets to resist easy dismissal. The tension shifts from "this one object breaks physics" to "the population statistics look strained," and that is a more serious kind of problem. A single outlier can be noise, but a shifted distribution suggests a bias or a missing ingredient. LCDM can absorb outliers because rare peaks exist and cosmic variance is real. It struggles when the outliers become a distribution, because then the parameters must move, and parameter shifts ripple into other well-tested domains. To match early massive galaxies, you can increase star formation efficiency at high redshift, and you can do it in simulations with subgrid prescriptions. But that can overproduce stellar mass later, unless you also add compensating quenching, which must then be justified. You can reduce feedback strength so gas stays bound, letting halos convert baryons into stars more quickly. But then you risk making galaxies too compact and too metal-rich too quickly, and you may conflict with observed scaling relations at later times. You can invoke rapid early mergers, and mergers do happen frequently in the early universe. But mergers require enough massive halos to begin with, and halo abundance is set by the initial fluctuation spectrum constrained by the microwave background. You can tweak dust assumptions to reduce inferred ages and masses, because dust can mimic older populations by reddening the spectrum. But dust must come from somewhere, and early dust production is constrained by how quickly supernovae and evolved stars can supply it. You can invoke lensing more aggressively, and lensing is undeniably present in the universe's architecture, but then you predict more arcs and more foreground structures than surveys actually see, and you must explain why magnification would preferentially affect the most puzzling cases. You can argue the stellar models are wrong at low metallicity, because stellar evolution in extreme environments is uncertain. But then you must still explain why multiple independent analyses lean the same way, even when they vary assumptions and codes. Each attempted fix saves one piece and stresses another, and the stress is the story. The model becomes a quilt of compensations, and the seams start to show, not as a dramatic tear, but as a growing sense of fine-tuning. This is the emotional logic of the chapter, and it is deliberately quieter than a revolution. The discomfort is not that cosmology is broken, but that it is being asked to do too much across too many linked conversions with too little slack. Because LCDM is not only a story about galaxies, and it is not only a story about dark matter halos, it is a story about the whole expansion history, the microwave background, and the cosmic web. And those pieces have been fit together with impressive consistency. If you change early structure formation, you touch ionization timing, and you touch the ultraviolet background that keeps intergalactic gas ionized. You also touch the small-scale power spectrum, because early halo abundance depends on how much primordial structure exists at small scales. If you change baryonic physics enough, you risk losing the clean fit to the cosmic microwave background, where LCDM is strongest. The early universe is where the model feels most secure, which is why early anomalies feel like they are knocking on the front door. That is why the phrase "should not exist" lands with weight, even when scientists say it carefully. It points at the model's proudest region, not its messy edges, and it forces a recheck of assumptions that usually stay invisible. The community response is cautious and technical, because the stakes are high and the history is sobering. Astronomy has seen anomalies evaporate before, and it has also seen anomalies mature into new physics, but only after relentless verification. Caution does not mean indifference, and it does not mean the results are being brushed aside. When enough anomalies point in the same direction, experts start to ask whether the yardsticks are drifting and whether the drift is coming from the data or the theory. The yardsticks here are the conversions we take for granted, and they form a ladder. Redshift to distance, flux to luminosity, luminosity to mass, mass to halo. Each rung is defensible, yet each rung has assumptions that can tilt the climb. Webb's deep fields forced those conversions into the foreground, because they pushed into a regime where small biases become large conclusions. They made the hidden assumptions visible and therefore contestable, which is what a good stress test does. At conferences and in papers, the language stays measured, because measurement is the culture and understatement is the habit. But privately, the reaction can be sharper, because pattern recognition is human, and experts know what too many feels like. A Nobel Prize winner looks at the early results and hears a deeper implication, not a headline, but a structural warning. If the early universe is assembling too fast, the baseline story is strained, and the strain will not stay confined to one subfield. The quote arrives like an inciting incident, because it gives voice to a thought many are trying not to indulge. This is not our universe. Taken literally, it is wrong, because the photons are real and the sky is the sky, and Webb is not hallucinating. Taken psychologically, it is precise, because it names a mismatch between the universe in our equations and the universe in our detectors. It means the universe in our models is not mapping cleanly onto the universe in our measurements, and that mismatch has a particular flavor. It means the model is losing its monopoly on plausibility, not because it has failed everywhere, but because it is being challenged where it expects to win. The line is not a call for panic, and it is not a demand for a new cosmology overnight. It is a marker for when an expert stops blaming single data points and starts suspecting a systematic tension, the kind that survives careful cleaning. This is the moment the documentary pivots from discovery to diagnosis. We stop asking what Webb saw and start asking what we assumed, because assumptions are the quiet machinery behind every plotted point. If early galaxies look too mature, either the universe built structure faster, or our inferences are biased, or the background cosmology is off. And if the background cosmology is off, the implications propagate forward, because the clock and the ruler are the same instrument. Distances change, ages change, and the expansion history becomes suspect, which is why this chapter cannot end with galaxies alone. The deep fields are not merely pretty images, they are measurements that lean on the same scaffolding used across cosmology. That suspicion has a name in the modern literature, and it has been building for years alongside other precise surveys. It is the Hubble tension, where two methods measure two incompatible expansion rates, and the disagreement refuses to shrink with better data. So the next step is not another deep field, and it is not a louder claim about impossible galaxies. The next step is to interrogate the ruler we use, to turn redshift into time, and to ask why the ruler reads differently depending on how you hold it. We began with a crowded mile 5 and a comforting model where the race felt familiar and the splits made sense. We end with a crowded deep field and a clock that may be miscalibrated where the numbers are consistent yet unsettling. In the next chapter, the question tightens, because the stakes are no longer confined to early galaxies. If our yardsticks are wrong, how wrong are they, and why do they disagree now? Now return to the race. The pack is still dense, but two official clocks disagree, and the gap is too large to dismiss as a casual glitch. Cosmology has a version of that contradiction, and it has a name that sounds almost polite. The Hubble tension is a persistent mismatch in the universe's expansion rate, measured with methods that should ultimately converge. The expansion rate today is called h0, the Hubble constant. It sets how fast distance grows per unit distance right now, which is the plain language meaning behind the formal units. Those units matter because they encode the claim. Kilometers per second per megaparsec means that for every megaparsec of separation, space adds a certain recession speed, even when nothing is moving through space. In a clean model, different ways of measuring R0 converge as data improve. In our universe, the opposite has happened, and the disagreement has become sharper as the error bars shrink. Tension is not a vibe word or a headline trick. It means statistically stubborn disagreement that survives better calibration, larger samples, and repeated cross-checks across independent analysis pipelines. In practice, tension means the likelihood curves refuse to overlap. Even after you account for known uncertainties, the two answers sit apart like parallel tracks that never meet. One ruler is local and late time, built from objects we can measure directly. The other ruler is early time, inferred from the infant universe's imprint on the sky. Late-time teams measure h0 by building a distance ladder. They start with geometry, climb through standard candles, then connect to supernovae that reach far into the expanding cosmos. The logic begins with parallax, the simplest distance tool we have, because it is pure geometry. Earth's orbit shifts a star's apparent position against background stars, and that tiny angle gives distance. Visually, parallax is a slow, patient wobble, stars tracing minuscule ellipses over months as our viewpoint changes. The angles are so small that milliarc seconds become the currency of cosmic measurement. Gaia made parallax precise for huge numbers of stars. That precision is the foundation under every higher rung, because a small offset in parallax becomes a systematic tilt in everything built above it. Gaia's catalogue is not just large, it is internally consistent in a way earlier astrometry could not match. It also forces astronomers to confront subtle effects like instrument calibration drift and global zero-point offsets. From parallax, the ladder moves to Cepheid variables. Cepheids pulse with a period that correlates with intrinsic luminosity, a relationship discovered in the early 20th century by Henrietta Leavitt. Leavitt's insight was simple and revolutionary. If period predicts true brightness, then a Cepheid becomes a beacon with a built-in wattage label, provided you calibrate the scale correctly. If you know a Cepheid's true luminosity, you compare it to observed brightness. That gives distance to its host galaxy once you correct for dust absorption and the way filters sample the star's spectrum. Cepheids are bright enough to be seen in nearby galaxies. They bridge the gap between local geometry and extragalactic scales, turning the Milky Way's parallax grid into a map that reaches beyond our neighborhood. A parallel rung uses the tip of the red giant branch, the TRGB. Old red giants reach a predictable maximum brightness before helium ignition, a sharp feature created by stellar physics rather than stellar youth. In a color magnitude diagram, the red giant branch rises like a cliff face, then ends abruptly at the tip. That edge is the measurement, an astrophysical stop line that can serve as a standard candle. TRGB stars behave differently from Cepheids and live in different galactic environments. That makes TRGB a valuable cross-check against shared biases, because it relies on older populations and different systematics. Once a galaxy's distance is known from Cepheids or TRGB, type Ia supernovae enter. SNE Ia are bright enough to be seen far away, and their flash briefly rivals the light of an entire galaxy. Type Ia supernovae are treated as standardized candles after light curve corrections. Their peak brightness correlates with how quickly they fade, which lets astronomers standardize something that is not perfectly standard. Under the hood, the physical picture is a white dwarf pushed toward instability, likely by accretion or merger. The details remain debated, yet the empirical regularity of their light curves is remarkably useful. They extend the ladder deep into the Hubble flow. That is the regime where recession from expansion dominates over local motions, so the cosmic signal rises above the gravitational noise of neighborhoods. The Hubble flow is where H0 is meant to be read cleanly. You want galaxies far enough away that peculiar velocities are a small correction, not a dominant term that can distort the slope. So the late-time measurement is a chain. Parallax calibrates Epheids, or TRGB, which calibrate SNE-Ea, which calibrate H0 as the slope of distance versus redshift. This chain is powerful, but it is also vulnerable to correlated systematics. A small bias at the bottom can propagate upward, and by the time it reaches supernova distances, it can masquerade as cosmology. Systematic errors do not look like random scatter that averages away. They look like a consistent tilt that survives more data, because the same hidden assumption keeps pushing in the same direction. Cepheids can be affected by metallicity, dust, crowding, and blending. In dense fields, multiple stars can masquerade as one brighter star, which makes the galaxy seem closer than it really is. Dust is especially treacherous because it reddens and dims light in a wavelength-dependent way. If the dust law is slightly wrong, the correction can shift distances by percent-level amounts without obvious alarms. Metallicity matters because it changes stellar atmospheres and pulsation properties. A Cepheid in a metal-rich spiral arm is not photometrically identical to one in a metal-poor environment, even if their periods match. Teams fight this by observing in infrared, by modeling crowding, and by comparing independent photometry pipelines. They also use different host environments to test sensitivity, looking for residual trends with color or location. Infrared helps because dust becomes more transparent at longer wavelengths. It also reduces the amplitude of Cepheid variability, which can simplify some corrections while complicating others. TRGB has its own risks, including population effects and contamination. Teams select halo fields to reduce crowding and to isolate old stellar populations, where the tip feature is cleaner and less blended. Even then, the measurement is a statistical edge detection problem. You are not measuring one star, you are measuring the collective cutoff in a luminosity function, and that requires careful completeness modeling. Supernovae bring additional systematics, including selection bias and host galaxy correlations. Surveys correct for these, but corrections can become part of the inference, especially when the sample spans different instruments and cadences. A flux-limited survey preferentially finds brighter events at higher redshift. If that bias is not modeled precisely, the standardized brightness can drift with distance in a way that mimics changes in H0. The ladder community has spent years trying to kill its own result. They swap calibrators, reprocess data, and tighten priors to see if H0 falls, because a fragile result would not survive that kind of stress test. Instead, the local value stays high. Typical late-time results cluster near the low to mid-70s kilometers per second per megaparsec, with uncertainties that are now small enough to make the disagreement unavoidable. On screen, the visual is almost too simple. Two bars with error whiskers sit apart, and the empty space between them becomes the story. The other ruler begins far earlier, long before stars existed. It starts with the cosmic microwave background, the CMB, which is less a photograph than a fossil imprint of early physics. The CMB is the afterglow from when the universe cooled enough for electrons and protons to form neutral hydrogen. Photons decoupled and have been streaming ever since, stretched by expansion into microwaves. That moment, recombination, happened about 380,000 years after the Big Bang. Before it, the universe was an opaque plasma, and light could not travel freely through the charged fog. Those photons carry tiny temperature variations across the sky. The pattern is not noise. It is a map of acoustic waves in the primordial plasma, with hot and cold spots reflecting overdensities and rarefactions. Before recombination, photons and baryons were tightly coupled. Gravity tried to compress matter. Radiation pressure pushed back, and sound waves rippled outward, like pressure waves in a drumhead made of light. The competition between gravity and pressure sets a characteristic scale. It depends on the baryon-to-photon ratio and on how quickly the universe expands, because expansion sets the time available for waves to travel. Those waves froze into a characteristic scale when photons decoupled. That scale is the sound horizon, a standard ruler imprinted at last scattering, and it becomes a geometric yardstick for the cosmos. In the CMB power spectrum, this ruler appears as acoustic peaks. Their positions and heights encode the universe's contents and geometry, and they also reveal how matter and radiation shared the early energy budget. The first peak is tied to the largest compression mode that had time to form. Subsequent peaks trace alternating compression and rarefaction, and their relative heights carry the signature of baryons loading the oscillations. The peak pattern depends on baryon density, dark matter density, and the overall curvature. It also depends on the primordial fluctuation spectrum, which is often summarized by an amplitude and a spectral tilt. Planck measured the CMB with extraordinary precision. Under LCDM, Planck's best fit parameters imply a specific H0, because the model links early densities to the later distance, redshift relation. This is not a direct measurement of today's expansion. It is an inference that runs through a model of the entire expansion history, translating angular scales on the sky into physical scales in space-time. LCDM assumes cold dark matter and a cosmological constant, plus ordinary matter and radiation. With those ingredients, the early universe ruler predicts the late universe rate, and it does so with impressive internal consistency. Planck's inferred H0 is lower, typically in the high 60s. The gap from the local ladder is around 9%, which is far larger than the quoted uncertainties on either side. 9% sounds small outside precision cosmology. Inside precision cosmology, it is enormous, because percent-level agreement is the expectation when the model is correct and the measurements are mature. The tension is not one paper versus another. It is a structural mismatch between two high-precision frameworks that should meet in the middle, like two survey teams mapping the same coastline from opposite directions. Historically, this is a strange reversal. The Hubble constant once varied wildly between groups, but the hope was that better detectors and better calibration would bring a single value into focus. Instead, the modern era produced two sharp answers. The disagreement is not a blur of ignorance. It is a crisp conflict between methods that each look carefully controlled. BAO adds a third voice, and it complicates the story further. Baryon acoustic oscillations are the same early sound waves, but measured in galaxy clustering later, after matter condensed into the cosmic web. BAO provides a standard ruler in the late universe. It measures distances as a function of redshift using the imprint of that primordial scale, visible as a preferred separation in the statistics of galaxies. Imagine a three-dimensional star map where galaxies form filaments and walls. Hidden in that structure is a faint, ring-like preference, an echo of the early sound horizon carried forward into the distribution of matter. When BAO is combined with Big Bang nucleosynthesis constraints, it tends to align with the lower H0. It reinforces the early universe ruler's story, because nucleosynthesis ties down baryon density through light element abundances. Big Bang nucleosynthesis is a separate relic of early expansion. The yields of deuterium and helium depend on the density of baryons and the expansion rate in the first minutes, so they act as an independent consistency check. So the universe gives two answers to the same question. How fast is space expanding today, as measured by local candles and by the early blueprint? If the latter is right, the early universe inference is missing something. If the early inference is right, the ladder is biased in a coordinated way, and the coordination would have to survive multiple independent rungs. The claustrophobia comes from the direction of progress. Better instruments should shrink disagreement, yet the disagreement persists and sometimes sharpens, as though the universe is refusing to be averaged into agreement. This is where Webb's context matters. Even when Webb is not measuring H0 directly, Webb pushes on the same calibration ecosystem that the ladder depends on, and it does so with infrared sharpness that changes what crowded means. Webb observes C-feeds in infrared with high resolution. It can reduce blending and refine zero points that feed into the supernova calibration, especially in galaxies where Hubble-era images left unresolved knots of light. In Webb images, spiral arms become textured. Star-forming regions break into individual sources, and what once looked like a single bright Cepheid can reveal faint companions that were quietly inflating its brightness. Webb also tests TRGB measurements in crowded galaxies. It can check whether the tip is being misidentified or biased by unresolved populations, and it can help separate old halo giants from younger interlopers. Each improvement is meant to remove excuses. Each improvement reduces the room where a hidden systematic can hide, because the ladder's weak points are increasingly illuminated from multiple angles. If a systematic remains, it must be subtle and coherent. It must shift distances by a few percent without leaving obvious fingerprints in residuals, and it must do so across different stellar populations and host galaxies. That is possible in principle, because astronomy is hard. Photons arrive, after traveling through dust, across detectors with quirks, and into pipelines that must model the sky with finite resolution. But the burden rises as independent ladders converge on the same high value. When different calibrators point in the same direction, the space for a single mundane explanation starts to collapse. Cepheid-based ladders and TRGB-based ladders are not identical. Their agreement suggests the problem is not a single astrophysical nuisance, because the nuisance would have to affect both methods in compatible ways. On the early side, Planck is not the only dataset. Other CMB experiments and lensing measurements broadly support the same parameter region, even if their error bars are larger and their systematics differ. The early inference is also cross-checked by BAO. BAO ties the sound horizon to the late universe's geometry in a way that is difficult to fake, because it uses large-scale structure rather than stellar astrophysics. So the tension is not a simple argument about one instrument. It is a conflict between a local geometric chain and a global early universe blueprint, and both are anchored in physics we think we understand. LCDM is the bridge between those domains. The model's job is to connect early conditions to late outcomes with one consistent expansion history, so that a ruler imprinted at recombination predicts distances measured by supernovae. A persistent mismatch implies either hidden systematics or missing physics. Those are the only two categories, and both are expensive because they force revisions to methods or to the model itself. If it is systematics, then our best distance tools are less trustworthy than we thought. That would ripple into galaxy masses, ages, and the cosmic timeline, because distance is the conversion factor for almost everything we infer. Distances set luminosities, and luminosities set stellar populations and star formation rates. A few percent shift in distance can quietly reshape the inferred history of galaxies across billions of years. If it is missing physics, then the simplest cosmological model is incomplete. That would ripple into dark matter, dark energy, and the growth of structure, because the expansion history is the stage on which everything evolves. The proposed fixes fall into recognizable families. Each family tries to change the inferred H0 without breaking everything else, which is the hard part because the data are interconnected. One family changes the early universe. The goal is to shrink the sound horizon, so the same observed angles imply a higher H0 today, effectively changing the size of the ruler rather than the reading of the ruler. Early dark energy is the flagship idea in that family. It adds a temporary energy component before recombination that speeds expansion briefly, then fades so that the late universe looks roughly like LCDM. Faster early expansion gives sound waves less time to travel. That reduces the sound horizon, shifting the ruler that anchors CMB and BAO, and allowing the same angular peak spacing to correspond to a higher present-day expansion. With a smaller sound horizon, the CMB can be fit with a higher H0. The tension relaxes, but the model gains new parameters and new tuning, and the question becomes why that component turns on and off when it does. Early dark energy is not free. It changes the epoch of matter-radiation balance and alters the growth of perturbations, which means it can affect the later distribution of galaxies and the lensing of the CMB itself. Those changes show up in structure formation. They can worsen the S8 tension, where predicted clustering amplitude can be too high compared to some late-time probes, creating a second argument even as the first one softens. Another family adds extra-relativistic species. This is often described as extra-neutrino-like components, sometimes parameterized as DNEF, which effectively increases the radiation energy density in the early universe. More radiation energy density also speeds early expansion. It can reduce the sound horizon and push inferred H0 upward, but it also changes the detailed shape of the CMB spectrum in ways Planck can detect. Extra radiation affects Big Bang nucleosynthesis. It changes helium and deuterium yields, which are measured and tightly constrained. So the allowed room for additional species is limited by chemistry forged in the first minutes. It also affects the CMB damping tail and peak structure. Planck's precision makes large deviations difficult to hide, because the small-scale smoothing of anisotropies is sensitive to the expansion rate and particle content. Another family modifies gravity, or changes how dark matter behaves. If gravity differs on cosmological scales, the mapping from early to late can shift, because distances and growth respond to the gravitational law. Modified gravity can alter distance relations and growth rates, but it must evade solar system tests and match lensing and clustering data simultaneously, which is a narrow corridor to navigate. Some proposals alter dark energy itself. Instead of a constant L, dark energy could evolve with time, changing the late expansion history and potentially reconciling local distances with the early anchor. Evolving dark energy can move distances at low redshift, but it must still match supernova Hubble diagrams, BAO distances, and the CMB anchor. And it must do so without introducing instabilities or unphysical behavior. Late-time fixes often collide with BAO. BAO is a geometric constraint that ties together redshift, distance, and the sound horizon. So changing one part of the story tends to pull another part out of alignment. If you change late expansion without changing the sound horizon consistently, BAO residuals appear. The model starts to fail in a new place, and the rescue begins to look like a trade rather than a solution. There are also calibration shift ideas. Maybe the supernova absolute magnitude is off, or the parallax 0 point is biased, or dust laws are mismodeled and the ladder's high H0 is an artifact of compounded small errors. These are plausible because the ladder is complex, but the ladder is also redundant, and redundancy is designed to expose exactly this kind of drift, by letting different rungs disagree if one is contaminated. A calibration shift big enough to erase 9% must be both large and invisible. It must evade internal consistency checks across multiple rungs, and it must do so across different telescopes, filters, and analysis teams. That is why the feeling becomes claustrophobic. Every escape route seems to narrow as the data become cleaner, and each new cross-check turns into another locked door. The Hubble tension is existential for LCDM because LCDM is a minimal bridge. It uses a small parameter set to connect early and late observations, and that simplicity is part of why it became the standard model. If the bridge fails, the model is no longer a universal map. It becomes a local fit that works in some regimes and not others, which is a very different kind of scientific confidence. That is the same theme Webb keeps provoking. A model that looked globally secure may be a patchwork of local successes, stitched together by assumptions that only reveal their seams under higher resolution. And the stakes are not only academic. If our expansion history is uncertain, then our inferred ages and timelines become uncertain too, because H0 sets the overall scale for how long the universe has been expanding. Cosmic age enters every story about when galaxies formed and how fast structure grew. It also shapes how we think about long-term cosmic futures, because acceleration determines whether the universe becomes emptier and colder faster. In the Great Filter metaphor, the physics matters because it sets the course. If the course is mismeasured, our confidence about where we are is miscalibrated, and we may mistake a temporary calm for a permanent trend. A civilization at mile 5 can misread the terrain if the markers are wrong. It can confuse early smoothness with a reliable map of the whole route, and it can underestimate the turns that come later. The Hubble tension is a marker that the map may be inconsistent. Two rulers are measuring one universe, and they do not agree. Even though both rulers are built from physics, we can test in other settings. If both rulers are honest, then the universe is telling us something structural. The standard model is missing a piece that connects early and late, or it is misusing a piece we thought we had already nailed down. That missing piece might live in the first minutes, in the first 380,000 years, or in the last few billion. Wherever it lives, it changes the story, because it changes how we translate observations into a single, coherent history. Now the narrative pressure shifts. If the expansion history itself is in dispute, then the driver of late-time acceleration becomes the next suspect, because acceleration is where LCDM makes its boldest claim. Dark energy is the name we gave to whatever makes expansions speed up. If our measurements disagree, dark energy may be simpler than L, or stranger than L, and the distinction matters for the fate of the cosmos. In the next chapter, we follow that suspicion directly. We ask whether dark energy is constant, or whether it is drifting under our feet, subtly changing the rules while we are still learning to measure the track. And if it is drifting, then the universe is not only expanding, it is changing its rules as it runs, and the clocks at the finish line may be telling us that the race itself has evolved. Now return to the race. The clocks disagree, and now the track itself looks unstable. In earlier chapters, we treated the universe like a course with fixed mile markers, yet the newest measurements hint the markers may slide. Chapter 3 left us with two rulers and one universe, refusing to reconcile. The obvious suspect was calibration, because calibration is where human error hides best. Astronomers know this lesson intimately. Small offsets in photometry, selection, or dust modeling can masquerade as new physics. But the deeper suspect is darker because it lives inside the equations. The thing we used to glue the model together may be changing with time. Acceleration was LCDM's cleanest claim, and it was also its most dramatic reveal. In the late 1990s, supernova teams expected to measure deceleration because matter should slow expansion. Instead, distant Type Ia supernovae looked too dim, implying the universe had expanded more than expected. That result was not merely a parameter update, it flipped the sign of the cosmic story. LCDM said the late universe is simple, dominated by a constant vacuum energy. It said the future is a smooth slide into emptiness, with galaxies drifting beyond reach as horizons tighten. It said the past can be reconstructed with a small set of fixed numbers, like a lock combination that never changes. The model's elegance came from that steadiness, because steadiness makes prediction feel safe. That confidence is why the next dataset matters. Not a telescope studying a few rare objects, where selection bias can hide in the sample. Instead, a survey mapping the statistical skeleton of the cosmos, where the average becomes a test of the rules. If the model is wrong, it should fail in the mean behavior, not only in the extremes. DESI is built for that average, and it is built with an engineer's impatience for small samples. The Dark Energy Spectroscopic Instrument sits on the Mayol 4-meter telescope at Kitt Peak, where desert air and dark skies turn nights into data. Its wide-field corrector feeds a focal plane packed with thousands of robotic fiber positioners. Each tiny actuator swivels like a mechanical flower, placing a fiber precisely onto a target galaxy. The scale is industrial, but the goal is delicate. DESI targets galaxies and quasars by the millions, then measures their redshifts with repeatable pipelines. Those pipelines matter because reproducibility is how a statistical survey earns trust. Each redshift is a timestamp because redshift tags how much the universe expanded since the light was emitted. In plain terms, it tells us how long the photon has been riding the stretching of space. A spectrum is more than a barcode of lines. It is a physical signature of atoms, temperatures, and velocities, and it is also a ruler for cosmic expansion. When spectral lines shift toward the red, the shift encodes the scale factor change between emission and observation. DESI's strength is that it measures this shift over and over, across enormous volumes, with the same instrument and the same reduction logic. DESI does not measure dark energy directly, because dark energy is not a glowing substance. It measures the geometry and growth that dark energy controls, and it does so by turning the sky into a three-dimensional map. Angle becomes transverse distance, and redshift becomes radial distance once a cosmology is assumed. That map is not just a picture of where galaxies are sitting today. It is a record of how expansion stretched space across different eras, and how gravity tried to stitch matter back together. When the map is visualized, it looks like a living architecture. Filaments thread through darkness, clusters flare like knots, and voids open as vast, dim cavities. The cosmic web is not decorative, it is a fossil of competing processes. Gravity amplifies tiny, early fluctuations, while expansion dilutes and cools the universe, and the balance between them is measurable. The key is large-scale structure. Galaxies are not sprinkled randomly, because the early universe was not perfectly smooth. Quantum fluctuations, inflated to cosmic scales, seeded slight overdensities and underdensities. Over billions of years, matter fell into the overdensities, while underdense regions evacuated into voids. Change the expansion history, and you change the web's scale, its contrast, and the timing of its assembly. DESI's most famous handle on expansion is BAO. Baryon acoustic oscillations sound technical, but the idea is simple, and it begins with sound. In the early universe, matter and light were coupled in a hot plasma, where electrons and protons were not yet bound into neutral atoms. Photons scattered constantly off free electrons, and that scattering tied radiation pressure to ordinary matter. Gravity tried to compress overdensities, and radiation pressure pushed back, launching sound waves. These were not sound waves in air, but pressure waves in a relativistic fluid, traveling at a significant fraction of light speed. The wavefront moved outward from each initial overdensity, dragging baryons along, while dark matter, immune to radiation pressure, began forming deeper gravitational wells. Those sound waves traveled outward until recombination, when the plasma cooled enough for electrons and protons to form neutral hydrogen. At that moment, photons decoupled and streamed freely, becoming the cosmic microwave background. The pressure support vanished, and the wavefront stopped propagating efficiently. The waves froze into the matter distribution, leaving a preferred separation scale. The result is the sound horizon, imprinted as a faint bump in galaxy clustering. It is a standard ruler because its physical length is set by early universe physics that we can model with high precision. It depends on the baryon density, the matter density, and the expansion rate before recombination. In other words, it is a ruler forged when the universe was young, then carried forward as the universe aged. Bayo is not one visible ring in the sky, and that subtlety is part of its power. It is a statistical feature extracted from many galaxy pairs, because the imprint is weak for any single region. You measure how often galaxies appear separated by a given distance, then look for the excess at the BAO scale. The bump is small, almost shy, but with millions of galaxies it becomes precise. Precision comes from repetition, and DESI is built to repeat. The trick is to measure that ruler at different redshifts, because redshift slices correspond to different cosmic times. At low redshift, the BAO scale appears at one angular size and one redshift interval. At higher redshift, the same physical ruler projects differently, because the universe expanded differently between then and now. By tracking that projection, you reconstruct the expansion history as a function, not a single number. This makes DC a time machine in a specific sense, and it is important not to romanticize it. It does not watch expansion happen in real time, because cosmic change is too slow for human lifetimes. Instead, it infers expansion by comparing the same early ruler against late geometry at many epochs. It is the same logic as the CMB sound horizon, but applied across the cosmic web, where the universe provides many snapshots, supernovae measure relative distances through standardized brightness, and that relativity is both a strength and a vulnerability. Type Ia supernovae are calibrated as standardizable candles, but their absolute luminosity depends on calibration ladders and astrophysical corrections. BAO measures absolute distances through a ruler, once the sound horizon is fixed by early physics. Together they can pin down the shape of the distance, redshift relation, which is where dark energy hides. If the curve bends differently than LCDM predicts, the simplest constant begins to wobble. To understand the heresy, we need the symbol. L in LCDM is the cosmological constant, introduced by Einstein in 1917 as a term that could hold the universe static. When expansion was discovered, L became unnecessary, and Einstein reportedly regretted it, though the historical quote is complicated. Then, decades later, L returned with a new role, not to freeze the universe, but to accelerate it. That reversal is part of why the constant feels uncanny. Its meaning has changed while its symbol stayed the same. In the equations, L behaves like a constant energy density of empty space. It does not dilute as the universe expands, which is counterintuitive if you imagine energy as a substance in a container. But in general relativity, energy density and pressure both gravitate, and vacuum energy has a peculiar pressure. That pressure is negative, and negative pressure drives accelerated expansion. In fluid language, the link between pressure and density is summarized by an equation of state. That link is captured by W, defined as pressure divided by energy density. For a true cosmological constant, W equals -1 exactly. That value is not a fit convenience, and it is not a rounding choice. It is a conceptual claim about the vacuum, implying a very specific stress-energy form. If W equals -1, dark energy density stays constant over time. Matter thins out as space expands, because its density scales roughly as the inverse cube of the scale factor. Radiation thins out faster because expansion also redshifts photon energy, adding another factor. But L stays put, and that immobility is why it eventually dominates. In that future, acceleration continues, and the universe approaches a cold, empty, de Sitter-like fate. If W differs from -1, the story changes, and it changes in ways that touch both observation and theory. Dark energy could dilute, or it could grow, depending on the sign and evolution. If W is greater than -1, it resembles quintessence, a slowly rolling field whose energy density evolves. If W is less than -1, it resembles phantom energy, which can violate energy conditions and invite instabilities. Even the vocabulary, quintessence, phantom, signals that we are leaving the safe, static picture. But the bigger shift is not a constant offset. The bigger shift is drift. Drift means W changes with redshift, so the equation of state evolves over cosmic time. That turns dark energy from a number into a history, and histories demand mechanisms. It becomes another dynamical component, not a fixed background. And that is why the word constant starts to sound like a misnomer. DESI's early releases have pushed this question into the open, not by proclamation but by pressure. When DESI combines BAO with other datasets, some fits prefer W not equal to -1. Some parameterizations prefer a W that varies with time, bending away from the cosmological constant line. The preference is not yet a verdict, but it is a pattern that refuses to be ignored. It is the kind of pattern that makes scientists lower their voices and check their plots twice. This is where the suspense lives. LCDM's power came from minimalism because it fit diverse data with few parameters. A drifting W adds freedom, and freedom can fake a fit, especially when the data are noisy or subtly biased. So the first question is always whether the drift is real, or whether it is the universe letting us overfit noise. In a statistical world, even honest pipelines can be seduced by chance alignments. Yet the second question is sharper, because it points beyond statistics. If the drift is real, it is not a minor patch, like adjusting a calibration constant. It means the vacuum is not a static property of spacetime, at least not in the way LCDM assumes. It means the driver of acceleration has internal dynamics, and dynamics imply hidden degrees of freedom. Hidden degrees of freedom are where new physics likes to live. DESI's map makes that hard to dismiss as philosophy, because it is anchored in geometry. The BAO ruler anchors distances at multiple redshifts, and those distances are geometric facts once the ruler is calibrated. If the distance curve prefers a different shape, the inference is that expansion changed pace differently than expected. That is exactly what evolving dark energy would do, because it changes the Hubble parameter as a function of time. The usual way to express this is with a parameterization, and parameterizations are both tools and traps. Cosmologists often write W as W0 plus WA times a function of scale factor, with the scale factor encoding cosmic time. The details vary, but the meaning is consistent across the literature. W0 is today's value, and WA captures how it changes with time, often in a smooth, first-order way. In LCDM, W0 equals -1, and WA equals 0, and that point is a kind of ideological center. Every deviation from that point is a statement that the vacuum is not constant. Every non-zero way is a statement that the vacuum has a time derivative, however small. That is the drift, and it is why the constant begins to look provisional. If dark energy evolves, consequences cascade through the entire inference chain, because cosmology is an interconnected system. Distances shift because the integral of expansion rate changes along the light path. Ages shift because cosmic time is computed from that same integral, and the clock depends on the expansion history. Growth histories shift because structure formation depends on how long gravity had to work against expansion, and when it was allowed to dominate. This loops back to Webb's early galaxies, which were unsettling partly because of timing. Their inferred ages and formation times depend on the expansion history used to translate redshift into elapsed time. If the universe expanded differently at intermediate redshifts, the mapping from redshift to time changes. A galaxy at redshift 10 still sits early, but the exact number of available millions of years can move. That movement can be enough to soften attention or to sharpen it. It also changes how easy early structure formation is, because growth is not only about time, but about rate. The abundance of halos depends on the growth factor, which depends on expansion and the matter content. If dark energy was weaker or stronger at certain epochs, the growth of perturbations would speed up or slow down. That could ease some early assembly tensions, or it could worsen them by suppressing growth when galaxies needed it. The CMB is also pulled into the story, because the CMB is a projection from early to late. Planck's parameter fits assume a particular late-time behavior when projecting early physics to today. If dark energy evolves, the angular diameter distance to last scattering changes, which shifts how the acoustic peaks map onto the sky. To keep the peaks aligned, other parameters may shift in response. Matter density, H0, curvature, or even inferred neutrino effects. The model becomes a balancing act, not a single knob. That is why evolving dark energy is not an isolated tweak. It is a new degree of freedom that forces a global refit, and global refits can be treacherous. The model's internal consistency becomes a moving target because the same dataset can be fit in new ways. The question becomes whether the new freedom resolves multiple cracks at once or merely relocates them. A fix that moves the problem is not a fix, it is a reshuffling. There is also the matter of growth probes, which serve as an independent audit. Weak lensing surveys measure how mass clumps by distorting galaxy shapes, producing tiny coherent shears across the sky. Redshift space distortions measure how galaxies' peculiar velocities imprint anisotropy in clustering, because infall and outflow distort distances along the line of sight. Both are sensitive to the growth rate, which depends on expansion and on gravity's law. If DESI suggests a drifting W, growth probes become a cross-examination, and cross-examinations are where stories break. A change in expansion history should leave fingerprints in how quickly structures formed. If the fingerprints do not match, the drift may be a mirage, or it may be pointing to modified gravity instead of dark energy dynamics. Either way, the implication is that the simplest late-time picture is incomplete. This is why the community stays cautious, even when the plots look suggestive. A preference for W not equal to -1 can appear at modest significance, then fade with new data. Systematics can mimic evolution, especially when combining heterogeneous datasets with different selection functions. Even the choice of parameterization can bias the inference toward apparent drift, because smooth functions can force curvature into the fit. DESI's own analysis is careful about this, because a survey can be undone by its own machinery. The survey must model target selection, fiber assignment, redshift failures, and observational systematics that imprint artificial clustering. It must calibrate the BAO feature extraction and validate against simulations that include survey geometry. A small bias in the correlation function can push W in a preferred direction, and the universe will not warn you when that happens. Even the atmosphere and the instrument leave fingerprints. Seeing conditions change the effective depth, and sky brightness changes the signal to noise. Spectrographs drift with temperature, and detectors have subtle response variations. DESI corrects these effects, but correction is a form of modeling, and modeling is where assumptions enter quietly. Supernova datasets add their own complexities, and these complexities are not cosmetic. Different compilations have different photometric calibrations, dust corrections, and host galaxy correlations that can shift standardized luminosities. Selection effects favor brighter events at higher redshift, and the correction for that bias depends on survey design. Combining BAO with supernovae can tighten constraints, but it can also import hidden tensions. A drift signal could be the compromise between two datasets that disagree for mundane reasons. Planck adds another anchor and another potential mismatch, because it is both precise and early. If BAO plus supernovae prefer evolving W, Planck may resist, because the CMB is sensitive to the integrated distance to last scattering. The combined fit can become a negotiation among datasets, where the best fit is not a clean physical story. Sometimes the best fit is simply the least uncomfortable compromise. So the correct posture is conditional, and conditionality is not weakness. The hypothesis is under pressure, not crowned, and the difference matters. The significance levels matter, and so do look elsewhere effects, because many models are tried. A 2 sigma hint is not a revolution, even if it is narratively tempting. Science has learned, painfully, that seductive hints can evaporate. But hints matter when they align with a broader pattern, because patterns suggest structure. Webb pushed on early structure formation, where the schedule seemed too fast. The Hubble tension pushed on the expansion rate today, where local and global rulers should converge. Now DESI pushes on the driver of acceleration itself, where a constant should have been the safest assumption. The cracks are not identical, but they cluster around the same promise. LCDM claimed a stable bridge from early to late, and stability is exactly what is being tested. This is the moment the documentary pivots again, from a disagreement about one number to a disagreement about one concept. A constant is supposed to be the safest object in physics, because it is the thing you do not have to explain twice. If L is drifting, then the safest object is no longer safe. The unease is not only about a fit, but about what we thought the vacuum was. To keep the stakes clear, we should say what is not being claimed, because restraint is part of the story. No one is saying DESI has proven dark energy evolves, and no one is saying the cosmological constant is dead. The claim is narrower and more unsettling. The data may be asking for time dependence, and the simplest constant may be an approximation, like a straight line that only looked straight at low resolution. If it is an approximation, then the universe's fate is back on the table, and that is not a metaphor. With a true L, acceleration never ends, horizons tighten, and distant galaxies slip beyond causal contact. With quintessence-like evolution, acceleration could weaken, stall, or even reverse in extreme models, allowing structure to remain visible longer. With phantom-like behavior, acceleration could intensify toward a future singularity, where expansion becomes violent. The future is not just a philosophical question, because it is encoded in the same W history. Even without dramatic endings, the interpretive shift is huge, because it changes what counts as an explanation. A constant vacuum energy can be treated as a background property, like a fixed curvature scale in the equations. A dynamical field must be explained, with a potential, initial conditions, and stability against quantum corrections. It invites new couplings, new particles, and new fine-tuning problems. Because fields rarely stay quiet without a reason. It also changes how we read the past, and the past is where astronomy lives. If dark energy was different at moderate redshifts, then distances to galaxies at those redshifts change. That affects inferred luminosities, star formation rates, and the timing of galaxy quenching inferred from colors and spectra. It affects the calibration of secondary distance indicators that assume a background cosmology. The same photons arrive, but our translation of them into history shifts. This is where the great filter motif returns, quietly, Because timelines matter. Our confidence about where we are in cosmic time depends on the expansion history, and expansion history is what is being questioned. If the history is wrong, then our estimate of how long habitable epochs last can shift. The marathon markers might be misprinted, and the pack at mile 5 might be closer to the cliff than we think. What does it mean to plan if the clock that sets the era is still being debugged? Cosmology does not directly compute the probability of civilizations, and it does not claim to. But it sets the boundary conditions for every long-term story about energy, stability, and time. If the universe accelerates differently, the window for complex structures and long-lived stars may be reinterpreted. The filter metaphor becomes less metaphorical when the physics timeline is uncertain. When the background changes, every foreground story inherits the uncertainty. There is also a psychological consequence inside science, and it is not trivial. LCDM felt perfect because it was simple and predictive, and because it turned messy observations into a coherent narrative with a few numbers. If one of those numbers becomes a function, the model becomes less like a map and more like a fit. A map tells you where you are, while a fit tells you what curve passes through the points. That does not mean it becomes useless, and it does not mean the previous successes vanish. It means the era of easy certainty ends, and cosmology becomes more like weather than like clockwork. The universe may still be describable, but the description may require a deeper theory that explains why dark energy behaves as it does. If the vacuum has dynamics, then the vacuum has a story, and stories demand origins. DESI is not alone in this search, and that matters because independence is the antidote to self-deception. Future surveys like Euclid, the Vera Rubin Observatory, and Roman will map galaxies and lensing with different instruments and different systematics. They will test BAO, supernovae, and growth in parallel, and they will do so with new depths and new sky coverage. If the drift is real, it should survive these independent checks, and it should appear with consistent sign and scale. The immediate task is cross-validation, and it is painstaking by design. Compare DESI BAO with EBOS and earlier BAO measurements to see if the ruler agrees across generations. Compare with supernova compilations using different calibrations and watch whether the inferred curve shape holds. Compare with Planck and ACT and with CMB lensing reconstructions that probe late-time structure. Compare with weak lensing from DES, KIDES, and HSC, and check whether growth agrees with the same W history. If the drift persists, the next task is interpretation, and interpretation is where costs appear. Decide whether the effect is dark energy dynamics, modified gravity, or an unmodeled systematic shared across probes. Each option has costs, because each option touches other successes of the standard model. The universe does not give free parameters without demanding payment elsewhere, and the payment often comes as a new tension. The deeper narrative beat is that the model fails where it claimed certainty, and that is why the mood turns mysterious. It struggles with early structure formation, where initial conditions should control the schedule. It struggles with the expansion rate today, where local and global rulers should converge. Now it struggles with the cause of acceleration, where a constant should have been the simplest answer. The failures are not catastrophic, but they are precisely placed. At this point, the documentary's central question sharpens, because the cracks point beyond technique. If Webb is revealing breaks at the model's confident points, what does that imply about space and gravity? What does it imply about our ability to extrapolate from local success to global truth? What does it imply about the odds that a civilization can plan for a future when the background rules may evolve? The questions do not demand despair, but they do demand humility. Now the narrative pressure shifts from measurement to bookkeeping. If L is not constant, then why did it ever look constant across so many datasets and so many years? If it is constant, why is its value so small yet non-zero, perched between nothing and domination? Either way, the universe forces us into fine-tuning arguments where constants look like suspicious coincidences. The discomfort is not only that the numbers are odd, but that they are oddly timed. The next chapter follows that discomfort, because the drift is only the surface ripple. We ask why the model looked perfect for so long, and why its constants are so precisely set. We move from drift in dark energy to the deeper unease of tuning, coincidence, and the possibility that our equations are effective, not fundamental. In that possibility, LCDM is not wrong so much as incomplete, like a low-energy approximation to a larger rulebook. Now return to the race. The pack is still there, but the finish line may be drawn on a moving floor. If the floor moves, then every split time must be reread, and every strategy must be reconsidered. The universe is still running, and we are still measuring, but the course may be changing as we watch. The pack at mile 5 still feels reassuring, and the crowd noise still sounds like safety, even as the air thins and the rhythm of footfalls becomes hypnotic. Yet Webb keeps implying the course itself is strange, like the route was surveyed by someone who enjoys hidden gradients, the kind that only reveal themselves after your legs commit. We can picture it in the camera's language. A dense cluster of runners moves as one body, shoulders brushing, feet tapping in a steady rhythm, breath making little clouds in cold air. The road looks flat from eye level, but the altitude profile, seen from above, has sudden ramps that only appear later, and the shadows on the pavement hide their true pitch. Chapter 4 ended with drift. If dark energy is not constant, then the safest number in the model becomes a moving target, and the confidence we felt about the late universe starts to soften. A parameter that once behaved like a fixed signpost begins to act like a shifting wind, and the map that guided us becomes less trustworthy. This is where the story changes its kind of tension. The earlier chapters were about measurement, better telescopes, cleaner data, tighter error bars, and the quiet heroism of calibration. Now the narrative pressure shifts from measurement to bookkeeping. We ask why the universe permits complexity at all, and why it permits it so precariously, as though the rules are balanced on a narrow edge. Fine-tuning is not mysticism, and it is not code for design. It is parameter sensitivity in equations that otherwise look ordinary, the way a stable bridge can depend on a few millimeters in a key joint. The mathematics is familiar, and that familiarity is part of the unease, because it means the fragility is not a poetic metaphor. You take the model's constants and initial conditions, then you nudge them slightly and you ask what survives. In many cases, the result is a universe that cannot build long-lived structure, not because of drama, but because the basic processes never get traction. The unsettling part is not that life is special. The unsettling part is that chemistry and stars sit on narrow ledges, and those ledges appear in multiple, unrelated places. Think of 26 locks on a door. Each lock is a constant or cosmological parameter that must land in a workable range, and the workable range is often a thin slice of what the equations allow. We do not mean 26 as a sacred inventory. We mean a clustered feeling that the door has many independent points of failure, and that the failures do not compensate for one another. If too many locks fail, you do not get fewer civilizations. You get no stable nuclei, no stars, or no galaxies, and the absence is structural rather than tragic. The universe does not merely become quieter, it becomes a place where complexity cannot even start, because the scaffolding never stands and there is no stage for later stories. Start with the cosmological constant problem, because it is the loudest mismatch between theory and observation. Quantum field theory predicts vacuum energy contributions that are absurdly larger than what cosmology infers, and the mismatch is not a small embarrassment. Depending on how you cut off the calculation, it can be off by dozens of orders of magnitude, and the number is so extreme it feels like a bookkeeping error with teeth. In plain terms, the vacuum in quantum theory is not empty. Fields have zero-point fluctuations, and each mode contributes a little energy, like countless tiny springs that never fully rest. When you add those contributions naively, the total vacuum energy density comes out enormous, so enormous that space-time should curl up violently, leaving no long, cool era for galaxies to assemble. Observed L is tiny in particle units, yet it is not zero, and that not zero matters, because gravity integrates small things over cosmic time. It is also timed to matter domination in a way that feels coincidental, because it becomes dynamically important only after billions of years of cosmic history. We live in the era when dark energy and matter are comparable, and that timing is part of the locked room atmosphere. If L were larger and positive by even modest factors, accelerated expansion would begin earlier, and the universe would stretch itself smooth before it could wrinkle. Density fluctuations would be pulled apart before they could grow into galaxies, and the cosmic web would remain a faint mist. Gravity would still pull, but it would be pulling on a fabric that is being yanked away faster than clumps can form. If L were negative and large in magnitude, the universe could recollapse quickly. You get a short-lived cosmos with little time for heavy elements, because stars require long, stable epochs to forge carbon, oxygen, and iron. In that case, the story ends not with emptiness, but with a premature crunch, and the clock runs out before chemistry diversifies. Cosmology cares because structure formation is a race between gravity and expansion. L sets the late-time pace, and pace determines whether clumps ever win, which is why a small energy density can dominate the plot. The equations for linear growth make this explicit. Overdensities grow when the expansion rate allows gravity to amplify them, and they stall when expansion dominates, freezing the universe into a thin, unfinished pattern. In visual terms, imagine two curves on a graph. One curve is the growth of structure, rising slowly like a tide that needs patience and time. The other is the expansion rate, flattening or steepening depending on L, and it is the curve that can quietly outrun everything else. A small change in L can move the crossing point, and that crossing point decides whether galaxies ever become common. Then there is dark matter abundance, another lock tied directly to Webb's story about early galaxies. Too little dark matter and baryons struggle to fall into deep potential wells, because ordinary matter is slowed by radiation pressure in the early universe. Dark matter, being effectively collisionless, starts clumping earlier and provides the gravitational wells that later collect gas, turning invisible mass into visible structure. Too much dark matter and structure forms early and dense, changing merger histories and radiation backgrounds in ways that can be punishing. Either extreme can disrupt stable disk galaxies and long-lived habitable environments, because violent mergers and intense early starbursts reshape galaxies into harsher places. The point is not that one value is nice. The point is that the window for familiar, quiet galactic neighborhoods may be narrow, and narrow windows invite the language of locks. Add the amplitude of primordial fluctuations, often summarized as Q near 10 to the -5. This is the tiny fractional variation in density imprinted in the early universe, visible today as subtle temperature anisotropies in the cosmic microwave background. Those anisotropies look like a speckled pattern on an otherwise smooth sky. an infant universe with freckles, where each freckle is a seed of later gravity. If Q is smaller, gravity never amplifies seeds into galaxies. The universe remains nearly uniform and without density contrasts. Gas does not gather into stars because nothing provides a preferred place to fall. The night sky would be dark, not because of dust, but because there would be almost nothing to ignite, and the darkness would be a physical consequence of smoothness. If Q is larger, the universe becomes violently clumpy. You get early black holes, frequent catastrophic encounters, and fewer quiet niches because dense regions collapse fast and produce intense radiation fields. The cosmic landscape becomes a place of rapid, chaotic assembly rather than slow, stable evolution, and stability becomes the rare resource. These are not philosophical statements. They are consequences of the same perturbation growth equations used to interpret CMB peaks and large-scale structure, the same tools that let cosmologists infer matter content from ripples. The same math that fits the acoustic peaks also tells you what happens when you slide the parameters, and it tells you that some slides erase the stage. Now zoom inward from cosmology to microphysics, because the locks do not stop at the horizon scale. Chemistry depends on mass ratios and force strengths, and those are written into the standard model as numbers we measure rather than derive. The universe does not only need galaxies, it needs atoms that can share electrons, store energy, and build long chains. Because complexity is built from reliable bonds. The electron-to-proton mass ratio sets atomic sizes and molecular vibration scales. Change it significantly, and stable chemistry shifts or collapses because electron orbitals and bond energies scale with the electron mass, and the periodic table's familiar spacing stops being familiar. A heavier electron shrinks atoms and raises typical chemical energies, while a lighter electron makes atoms puffier and bonds weaker. And either shift changes how molecules survive heat and radiation. This ratio also sets how molecules absorb and emit infrared radiation. That matters because planetary climates depend on vibrational modes, greenhouse absorption bands, and the ability of gases to move heat. A small change in microscopic masses can echo upward into atmospheric physics, where habitability lives or dies, and the echo is not subtle when you integrate it over geologic time. The fine structure constant sets electromagnetic coupling. If it is too large, electron orbits tighten, and nuclear reactions and chemistry change together, because the Coulomb barrier in nuclei becomes harder to overcome. Fusion in stars depends on tunneling through that barrier, and stronger electromagnetism makes tunneling less probable at the same temperatures, which forces stars into different sizes and lifetimes. If it is too small, bonding weakens and complex molecules become fragile. The periodic table becomes less useful as a platform for complexity, because the energy differences that stabilize diverse chemical structures shrink. Chemistry becomes a flatter landscape, with fewer robust valleys where information-rich molecules can persist, and fewer ways to build redundancy against noise. The ratio of electromagnetic to gravitational strength is another lock, because it sets the basic scale separation between atoms and stars. Gravity must be weak enough for stars to be large and long-lived, so that they burn fuel slowly and provide stable light for billions of years. In a universe where gravity is stronger, the same mass compresses more, raising core temperatures and accelerating fusion, and the calm Middle Ages of stars become scarce. If gravity were stronger by a modest factor, stars would burn hotter and faster. Long main sequence lifetimes would shrink, and stable climates would be harder to sustain because the window for biological evolution would narrow. The sky might be bright, but it would be bright in short pulses of stellar youth, and the long, patient illumination we rely on would be rarer. If gravity were weaker, gas clouds might not collapse efficiently. Star formation could become rare, and heavy element production could stall because fewer stars means fewer furnaces for nucleosynthesis. The universe could have plenty of hydrogen and helium, yet lack the metals that make rocky planets and complex chemistry possible. And it would look spacious, but chemically unfinished. Now move to the nuclear locks, where the feeling of a trap becomes sharper. Stable nuclei require a balance between the strong force, electromagnetism, and quark masses, and that balance is not negotiable in any simple way. The strong interaction binds protons and neutrons, while electromagnetism pushes protons apart, and the quark masses set the detailed energy levels that decide which nuclei hold together. If the strong interaction were slightly weaker, deuterium could be unstable. Without deuterium, stellar fusion chains struggle to start, because the proton chain relies on intermediate steps that build deuterium as a gateway. The first rung of the ladder would be missing, and stars would have trouble climbing, leaving the universe with fuel but no reliable ignition. If the strong interaction was slightly stronger, diprotons could become stable. Stars could burn hydrogen too quickly, shortening lifetimes and changing stellar evolution, because the bottleneck that slows fusion in our universe would be removed. Our sun's calm, long burn depends on fusion being difficult enough to be slow, and difficulty here is a gift. The neutron to proton mass difference matters because it sets beta decay and nuclear stability. Shift it, and you change how much hydrogen survives after the early universe, because neutrons and protons interconvert in the first minutes after the Big Bang. The freeze-out balance, followed by neutron decay, sets the initial inventory of light nuclei, and that inventory becomes the raw material for everything else. Big Bang nucleosynthesis is sensitive to these balances. Small shifts can yield a universe with almost no hydrogen, or a universe with too much helium, because the reaction network is a competition between expansion rate, nuclear reaction rates, and the available particle populations. Those first 3 minutes are like a chemical factory running at extreme temperature, then shutting down abruptly, and the shutdown time is part of the recipe. Hydrogen scarcity is not a minor inconvenience. It removes water chemistry and long-lived hydrogen-burning stars, which are central to stable, habitable timescales. Without abundant hydrogen, you lose the simplest fuel and the simplest solvent, and you lose them at the same time, which is why this lock feels like it guards multiple doors. The carbon story is the lock people remember, because it has a name and a mechanism. It is the triple alpha process in red giant cores, where helium burning becomes a delicate choreography that depends on both temperature and quantum chance. In the deep interior of an aging star, temperatures climb until helium nuclei can collide often enough to matter, and the core becomes a dense, glowing laboratory. 2 helium nuclei form beryllium-8, which is unstable and decays quickly. A third helium must arrive before it falls apart, and that requires a resonant energy level in carbon-12. Without the resonance, the probability of the three-body process would be too small, and carbon would be scarce, leaving later planets with fewer molecular possibilities. That resonance is the Hoyle state. Its energy sits in a narrow window that makes carbon production efficient in ordinary stars, and it sits there like a tuned note in a musical instrument, precise enough to be noticed. The physics is not mystical. It is quantum mechanics, where nuclear energy levels determine reaction rates, and reaction rates determine what elements become common. Shift the resonance energy by small amounts, and carbon yield changes dramatically. Oxygen yield shifts too, because carbon then captures another helium to become oxygen, and the relative abundance of carbon and oxygen sets the chemical palette for later planets. The universe's chemistry is written in the branching ratios of stellar cores, and those ratios are written in energy levels. This is not a claim that carbon is uniquely privileged. It is a claim that stellar nucleosynthesis pathways can be resonance-dependent, and resonance dependence can create narrow corridors that are easy to miss until you compute them. When the corridor is narrow, it becomes natural to ask why the corridor exists at all, and why multiple corridors seem to align. A universe can be sterile without being empty. It can have stars and light, yet lack the chemical diversity needed for complex polymers and information storage, and the absence would be invisible from a distance. The camera could show a galaxy with glittering arms, but the narrator would know that the glitter is chemically monotonous, beautiful, yet barren, like a library of blank books. Now the narrative pressure shifts again. Fine-tuning is not one lock, it is a corridor of locks across scales, from the cosmic expansion rate down to nuclear-level spacings. The corridor is why the topic feels like a locked room mystery. You can list the locks, but listing does not explain why they align, and it does not explain why the list spans such different domains. The 26 number is a motif, not a sacred count. It stands for the cluster of parameters that appear independently adjustable in our current theories, and it stands for the sense that many of them matter at once. Some are dimensionless couplings. Some are mass ratios, some are cosmological densities and initial condition amplitudes, and the mix makes the corridor feel oddly cross-wired. The discomfort comes from how independent they look. In the Standard Model and LCDM, many values are inputs, not outputs, and the theory does not yet tell us why they take their measured forms. We measure them, then we proceed, because that is how effective theories function. Operationally it works, yet it leaves a question that keeps returning, especially when new data tighten the constraints. Why do the inputs land in the narrow region that permits long-lived stars, stable nuclei, and complex chemistry? Why does the universe sit near multiple apparent thresholds, where a small change flips the sign of possibility? When thresholds stack, the mind starts to suspect a pattern, even if it resists naming one. And even if it knows suspicion is not evidence. Historically, physicists have felt this kind of discomfort before. The pre-quantum atom had a bookkeeping crisis, because classical electrodynamics predicted electrons should radiate and spiral inward, draining energy in a fraction of a second. The crisis did not mean the data were wrong. It meant the conceptual ledger was missing a principle, and it took a new framework to make stability ordinary again. At this point, three broad responses dominate the serious conversation. Each response tries to dissolve the locked room without pretending the locks are imaginary, and each response carries a different kind of cost. None of them is a slogan, and none of them is free. First is chance. The constants are what they are, and we got lucky in a vast space of possibilities. A single winning draw with no deeper reason. Chance is logically allowed, and science does not forbid it, but it feels expensive. It asks us to accept extreme improbability without an underlying generator story, and to stop asking why the dice were rolled at all. There is also a subtle scientific discomfort with pure luck. In other contexts, when we see a narrow outcome repeated, we look for a mechanism that biases the outcome, because mechanisms are what science trades in. Here, the narrow outcome is not repeated across experiments. It is the single universe we can observe, which makes the inference fragile, and it makes humility mandatory. Second is necessity. A deeper theory fixes the values uniquely, and what looks tuned is actually forced by consistency, symmetry, or a hidden dynamical rule. Necessity is appealing because it restores inevitability, and it makes the universe feel less like a lottery ticket. It also raises the bar, because the deeper theory must explain why the unique solution permits complexity, rather than forbidding it. In practice, necessity often points towards symmetry, consistency conditions, or dynamical attractors. Symmetry can reduce the number of free parameters, and attractors can make diverse initial conditions converge on similar late-time behavior, even when the starting points differ. Yet the present state of physics does not give us a complete story that locks every dial into place, and the missing links are exactly where the unease collects. Third is selection, often called anthropic reasoning. We observe compatible constants because observers can only arise in compatible universes, and that conditional statement is logically hard to escape. Selection is not a proof of multiverses, and it is not a surrender. It is a statement about observation under survivorship bias, the same logic that warns you not to infer safety from survivors alone. If there is an ensemble of domains with varying constants, then most domains are empty. Observers appear only in the rare domains that pass the locks, and those observers will naturally report that the locks were passable. The explanation is not that the locks were designed for them. The explanation is that only they can speak, and silence elsewhere is part of the dataset. Selection can also operate without a literal multiverse in principle. It can be a statement about how we define the question and what counts as a random draw, because random is not a physical process until you specify the generator. Still, selection has a psychological cost. It can make the universe feel like a trap, because the very fact we exist becomes the explanation, and explanations that point back at the explainer can feel circular. It risks turning physics into bookkeeping of where life can happen, rather than why the laws are what they are. The danger is not that the logic is invalid. The danger is that the logic can become a stopping point, and science advances by refusing to stop too early, even when the next step is unclear. Now return to the race. Fine-tuning changes how we interpret a crowded field of habitable worlds, because it shifts attention from planets to the deeper stage on which planets appear. Earlier chapters used Kepler and TESS to increase the number of plausible starting lines, and the numbers were thrilling in their sheer abundance. More Earth-like planets should raise the odds of company, and the statistics of exoplanets still feel like good news, at least at first glance. But fine-tuning suggests a different bottleneck. The universe might allow many habitable planets, yet still enforce a near-universal breakpoint later, where complexity fails for reasons that are not obvious at mile 5. Habitable is mile 5, not the finish line. It means liquid water and stable energy flows, not durable intelligence, and not the long chain of contingencies that intelligence seems to require. The great filter logic does not care where the bottleneck sits. It only cares that the product of probabilities becomes tiny, because multiplying many small chances yields a vanishing result, even when the first terms look generous. You can have abundant planets and abundant chemistry, yet still have a near-zero outcome for long-lived civilizations, and the silence would still be the expected sound. A universe can be generous at the start and brutal later. It can produce oceans everywhere, then erase civilizations with a common failure mode, and the erasure could be quiet. It could be a failure to stabilize, a failure to coordinate, or a failure to survive its own energy use. And the quietness is what makes it frightening. The horrible possibility is not that aliens are hiding. The horrible possibility is that the statistics imply a barrier we have not met, and that we are still early in the course, running on fresh legs. If the universe is fine-tuned for complexity, it may also be fine-tuned for fragility. Complexity could be permitted, yet stability could be rare, and rarity does not announce itself. That fragility can be physical, not moral. It can be about energy gradients, entropy budgets, and the difficulty of sustaining coordination over long times. Because complex systems must continuously export entropy to remain ordered, and that export requires steady resources. A civilization is a thermodynamic machine as much as it is a cultural story, and machines fail at thresholds. The marathon metaphor becomes sharper here. A million runners at mile 5 means nothing if mile 20 contains a cliff, and the cliff is invisible from the starting line, hidden behind a bend. Fine-tuning is the clue that the course has cliffs. It tells us that many processes sit near thresholds where small shifts end the story, and that the endings can be simple. Civilizations might face analogous thresholds. Small shifts in behavior, technology, or environment could push them into irreversible collapse. The way small shifts in constants can erase stars or chemistry. That parallel is not a claim of cosmic intention. It is a warning about how systems behave near critical points, where feedback loops suddenly change sign. Now connect this back to Webb's discomfort. If LCDM breaks where it was most confident, then our list of locks may be incomplete or miscategorized, and the corridor may be drawn with the wrong map. Some locks might not be independent. Some might be shadows of a deeper constraint we have not recognized, and the apparent tuning could be a projection of missing structure, like a perspective illusion. Or we might be asking the wrong question. We treat constants as free dials because our theories are effective, not fundamental, and effective theories are built to work within a domain. They summarize deeper physics the way a weather forecast summarizes fluid dynamics, useful and accurate until you demand an explanation of every molecule, and then you discover what was averaged away. Effective theories hide the mechanism that sets the dials. They work within a regime, then fail when pushed beyond it. And that failure can look like tuning because you are trying to extend a local approximation into a global rule. Webb's early galaxies and the Hubble tension both push beyond comfortable regimes. They hint that our bookkeeping might be missing a term, and missing terms often masquerade as coincidences. If the bookkeeping is missing a term, then fine-tuning could be an artifact of our description. The locks might be labels on a door that is not actually locked, because the door is not a door at all. It could be a curtain, and the locks could be our mistaken attempt to fasten it, mistaking fabric for steel. But the opposite is also possible. The locks might be real, and our success in physics might be local luck, the way a map can be accurate in one city and useless in the wilderness. That is why the chapter's tone stays restrained. We do not need conspiracies, because the equations already create the claustrophobia, and the data keep tightening the walls. The universe looks like it permits complexity only in narrow corridors. Narrow corridors are where filters hide, because a filter does not need to be dramatic. It only needs to be common, and it only needs to be hard to see until you reach it, when turning back is no longer possible. Now the narrative pressure shifts toward a historical pattern in physics. When bookkeeping problems become intolerable, they often force radical ideas, not because scientists crave revolution, but because the ledger must balance, and prediction depends on balanced ledgers. The cosmological constant problem is bookkeeping. Fine-tuning across couplings is bookkeeping. Entropy accounting will become bookkeeping too, and it will do so in a place where gravity cannot be ignored. In the past, bookkeeping problems have led to quantum theory, to renormalization, to symmetry principles, and to new degrees of freedom. Renormalization, in particular, taught physicists how to separate what you can measure from what you cannot, while still making predictive sense, and it made field theory usable. Yet renormalization also sharpened the vacuum energy problem, because it made the subtraction feel formal rather than physical, like a cancellation without a cause. The next pivot is another bookkeeping crisis, but it arrives from gravity rather than particle physics. It begins with a simple question about information, posed in a way that refuses to be dismissed as philosophy. What is the entropy of a black hole? If a black hole swallows a library, where does the library's information go? And what does "go" even mean when space-time itself is part of the system? The visual can slow down here. A dark sphere hangs against a star field. not as an object with a surface, but as a region where trajectories end and where light cones tilt inward. A stream of light, then a spacecraft, then a box of books crosses an invisible boundary, and the outside universe is left with only mass, charge, and spin. The camera lingers on the boundary, the horizon, as though it is a line drawn by an accountant. Jacob Bekenstein treated that question as physics, not metaphor. He argued that black holes must carry entropy proportional to their horizon area, because otherwise, the second law of thermodynamics could be violated, and the violation would be operational. If you could throw entropy into a black hole and make it disappear, then the universe's accounting would fail, and thermodynamics would stop being universal. That claim sounds like a technical detail, yet it detonates our intuition about where reality lives. Entropy is a count of microstates, a measure of hidden possibilities, and Bekenstein was saying that a black hole has an enormous number of them. He was also saying that the number scales with area, not volume, which is the opposite of everyday expectations, and it hints that gravity measures information differently. It suggests the universe's deepest accounting happens on boundaries. The event horizon becomes a kind of ledger line, a surface that records what fell in, even if the record is encoded in a way we do not yet fully grasp. Later work, including Hawking's calculation of black hole radiation, would sharpen the paradox. Black holes are not perfectly black, and evaporation raises the question of whether information is lost or transformed. And if reality is boundary bookkeeping, then fine-tuning might be a symptom of emergent space. The locks might be constraints of a deeper holographic rulebook, where what looks like independent dials are actually linked by a hidden consistency condition, and the link is enforced by information limits. The corridor might be narrow because the underlying theory permits only certain coherent worlds, and coherence is stricter than we assumed. We leave this chapter with the door still closed, but with fingerprints on the locks. The next chapter follows the fingerprints to the horizon, where gravity and information begin to trade places, and where the ledger may finally explain the locks. We are still at mile 5. The pack is still dense. The course ahead is starting to look designed for attrition, even without an enemy, and the steepness is only beginning to show. Now the narrative pressure shifts from measurement to bookkeeping. Webb's early galaxies and the drifting expansion story both attack our confidence in the map, because they land exactly where the model looked most settled. Yet the deepest threat is not a new parameter, because it is a rule about information, about what the universe is allowed to forget. If the universe keeps surprising us where we were most certain, then we should ask what certainty was built on. Was it built on data or on an assumption that the bookkeeping always closes? Thermodynamics looks like bedrock because it is not optional, and it does not care about our preferred stories. The second law says total entropy never decreases in an isolated system, even when the system's details are violently rearranged. Entropy is not just disorder in a casual sense, because it is a count of microscopic possibilities consistent with what we observe. In plain terms, entropy measures how many hidden arrangements could be underneath the same visible state. That definition matters because physics is a machine that turns microscopic uncertainty into macroscopic prediction. When entropy accounting fails, prediction fails, because you no longer know which macrostates are allowed to occur. If the ledger can be cheated, then the universe can produce outcomes that look like free energy from nowhere. In laboratories, the second law survives every attempt to corner it, and that stubbornness is part of why it feels fundamental. Black holes used to look like simple objects in general relativity, almost offensively simple given how extreme they are. They were regions where escape becomes impossible once you cross the event horizon, a surface defined by light itself failing to get out. From far away, They were described by only mass, charge, and angular momentum, a result summarized as no hair. That simplicity was elegant, and it was also suspiciously blank, like a filing cabinet with labels but no files. Visually, the classical picture is clean and geometric. A dark sphere sits inside warped starlight, while the surrounding space-time bends like a stretched fabric under a heavy weight. The horizon is not a material shell, yet it behaves like a one-way boundary for causal influence. Outside observers can orbit, measure and wait, but they can't retrieve what has crossed. The accounting problem seemed obvious in hindsight, yet it hid in plain sight for decades. Drop a hot gas cloud, a star, or a library into a black hole, and the outside description becomes brutally compressed. From the outside, the detailed microstate information disappears behind the horizon, leaving only a slightly heavier black hole. If the information is gone from the observable universe, then entropy appears to decrease. That is not a philosophical worry, because you can engineer the setup and make the paradox quantitative. You can take a box of high entropy matter and lower it toward the horizon on a strong cable. You can extract work with a rope and pulley, using the black hole's gravity like a battery, then let the box fall in. If the outside world loses the box's entropy without compensation, the second law can be beaten. The thought experiment is vivid because it is so ordinary in its components. A box, a winch, a measured temperature, a careful lowering, then a clean release into darkness. The horizon does not flash or crack, and nothing dramatic seems to happen at the boundary. Yet the ledger line, if it exists, has just been asked to record a loss. In the early 1970s, Jacob Bekenstein treated this as a real crisis, not a word game about definitions. He argued that black holes must carry entropy, or thermodynamics would be violated by perfectly legal processes. The horizon had to behave like a thermodynamic object, even if it looked like empty geometry. The point was conservative. Save the second law, because without it, the rest of physics becomes unmoored. Bekenstein's key move was to tie entropy to the event horizon itself, because the horizon is what the outside world can actually track. He proposed that a black hole's entropy is proportional to the area of its horizon, not its volume or its mass alone. The horizon becomes a ledger line, where the universe keeps track of what fell in. As the black hole gains mass, the horizon area grows, and the ledger grows with it. The proposal sounded radical because it inverted ordinary intuition about where complexity lives. In everyday matter, entropy scales with volume, because volume holds degrees of freedom in the bulk. Double the volume of a gas at fixed density, and you roughly double the number of microscopic arrangements. Area is usually just a boundary, not the storage location, and boundaries are where we expect constraints, not capacity. Bekenstein's area law implied a limit on information in a region, and that implication was sharper than it first sounded. If the maximum entropy is set by boundary area, then the interior cannot hold unlimited independent data, even in principle. That is a new kind of constraint, and it does not resemble ordinary statistical mechanics. It suggests that gravity changes the rules of counting. At first, many physicists resisted the idea, because it looked like a category error dressed as a clever fix. Entropy belongs to microscopic states, and a classical black hole seemed to have none, because it was defined by smooth geometry. General relativity gave a horizon, not atoms on a surface, and not a lattice of degrees of freedom. The horizon looked like a coordinate artifact, not a physical membrane. There was also a conceptual discomfort that rarely gets said out loud. If entropy is real, then it should correspond to real microstates, and microstates should be countable in some underlying theory. But classical general relativity is not built from countable constituents, and it does not come with a natural notion of bits on a horizon. Bekenstein was asking the community to accept a thermodynamic quantity without yet knowing what it was counting. But the second law is stubborn, and Bekenstein's argument was built to be stubborn too. If you can throw entropy into a black hole, then either the second law fails or the black hole's entropy rises. The only place to put that entropy, from the outside perspective, is the horizon. The horizon is the only feature that reliably marks what the exterior has lost access to. Bekenstein also introduced a bound that sharpened the intuition, and it made the argument feel less like a patch. For a given energy and size, there is a maximum entropy that can fit without forming a black hole. Push beyond that, and gravity forces collapse, hiding the excess behind a horizon. Gravity becomes an information regulator, not just a force. The bound is conceptually simple, even when the math is not. If you try to cram too much energy into too small a region, space-time responds by creating a horizon, and the region stops being an ordinary container. It is as if nature enforces a maximum density of describable detail, and the enforcement mechanism is gravitational collapse. The universe does not merely discourage excess information, it quarantines it. Then the story collided with quantum theory, and the collision made the horizon physical in a way geometry alone could not. Stephen Hawking studied quantum fields near a black hole in curved spacetime, using the machinery of quantum field theory in a gravitational background. His calculation treated the vacuum as active, filled with fluctuations that cannot be ignored near strong gravity. Even empty space seethes with virtual excitations, and near a horizon, the bookkeeping of those excitations changes. The result was shocking because it made black holes imperfect, and it did so through a mechanism that sounded almost like a trick of perspective. Quantum effects near the horizon produce particle creation that escapes to infinity, while partner modes fall inward. To an outside observer, the black hole emits radiation with a thermal spectrum, as though it were a hot object. A black hole is not black, because it glows. For visuals, imagine the horizon as a dark rim surrounded by a faint, ghostly haze, like heat shimmer over asphalt at night. Particles appear as brief sparks, then stream outward in thin lines, while their partners vanish inward without a trace. The emission is not a jet and not an explosion, but a steady whisper of energy leaving the gravitational well. The silence of the classical horizon is replaced by a quantum hiss. Hawking radiation implies a temperature, and temperature implies entropy, because temperature is a measure of how energy is distributed among microstates. If a black hole has a temperature, then it must have thermodynamic properties, including heat capacity and an entropy that changes with energy. The horizon stops being a mathematical boundary and starts acting like a physical system. What looked like pure geometry now behaves like matter in one crucial respect. It can be warm. Hawking's temperature is inversely proportional to the black hole's mass, a scaling that is strange but internally consistent. Small black holes are hotter, and large black holes are colder, so the most massive holes are nearly at absolute zero by everyday standards. That inversion means evaporation accelerates as the black hole shrinks, because losing mass makes it hotter. Over fantastically long times, a black hole can lose mass by radiating energy away. This is where the thermodynamic analogy becomes more than analogy. If the black hole radiates like a blackbody, then it has an effective surface with an emissivity, even if that surface is not material. The horizon becomes a thermodynamic interface between the inaccessible interior and the accessible exterior. In the ledger metaphor, the horizon is not just a line on paper. It is the accounting department itself. Once temperature exists, the entropy formula becomes unavoidable, because the first law of thermodynamics links changes in energy to changes in entropy through temperature. Hawking and Bekenstein's ideas lock together into a single statement that no longer feels optional. The entropy of a black hole equals a constant times the horizon area, divided by the Planck length squared. Entropy is measured in units of fundamental area. This is the Bekenstein. Hawking entropy, and it legitimizes the area law with an authority that argument alone could not provide. It is not a metaphor because it comes from a concrete calculation in quantum field theory on curved spacetime. It makes the horizon's area behave like a count of microscopic degrees of freedom. It says the surface carries the bookkeeping, even when the surface is made of geometry. The Planck length enters like a signature, and it is a clue about what kind of physics is hiding underneath. The Planck scale is where quantum mechanics, gravity and relativity are all equally important, and where smooth spacetime is expected to break down. Dividing by the Planck length squared suggests that the horizon is tiled by fundamental patches, each patch carrying roughly 1 unit of information. The formula does not show the tiles, but it insists they exist. The formula also reveals the scale of the shock, because the numbers are enormous. A solar mass black hole has an entropy vastly larger than the entropy of the Sun, even though the Sun contains far more particles in the ordinary sense. The black hole looks simple, yet it hides an enormous number of microstates. The simplicity is not emptiness, because it is compression. In imagery, you can picture the Sun as a turbulent, boiling sphere of plasma, visibly complex at every scale. Then picture a black hole of similar mass as a clean, dark disk, with a smooth shadow and a bright ring of bent light. The paradox is aesthetic as well as scientific. The visually simpler object has the larger entropy. The universe is telling us that appearance is not a reliable guide to information content. Now the narrative pressure shifts again, from a paradox about black holes to a rule about reality. The area scaling is the conceptual turn that refuses to stay local, because it threatens our default way of thinking about space itself. In ordinary physics, the number of independent bits you can store in a region grows with volume, because you imagine filling space with cells. You assign each cell a degree of freedom, then count the cells, and the count scales like length cubed. Black holes say that strategy fails at the deepest level. The horizon behaves like a maximal storage device, and it behaves that way no matter what you try to store. Try to pack more information into a region than the area law allows, and you form a black hole, which hides the excess behind a horizon. The region's boundary becomes the limiting factor, not its interior. The inside cannot be more informative than the surface permits. This is why the result feels like an inversion of common sense, and why it lands with such force in narration. We live inside volumes, so we expect volume to be fundamental, and we build our metaphors around rooms, containers, and interiors. We treat surfaces as secondary because they are where things end, and endings feel like limits. The black hole result says the ending is where the counting happens. There is also a subtle shift in what information means in this context, and it is easy to miss. We are not talking about human-readable text, but about the complete specification of a quantum state, including phases and correlations. Entropy in this setting is a measure of how many distinct quantum configurations could correspond to the same macroscopic exterior. The horizon area is telling us how many such configurations the universe can hide without contradiction. The second law is the motive force in this story, and that matters for the documentary's motif. Bekenstein was not trying to rewrite space and time, and he was not chasing a fashionable speculation about simulation. He was trying to prevent thermodynamics from breaking, because thermodynamics is the language of irreversibility in a universe full of processes. The radical implication arrived because the ledger had to balance. Once you accept the area law, the next question becomes unavoidable, and it is almost uncomfortable in its simplicity. If a black hole is the densest possible information storage, then it sets a universal bound on entropy for any region. Any region of space has a maximum entropy proportional to its boundary area, not its contents. That bound does not care what is inside, because it is enforced by gravity. This is the seed of the holographic principle, and the seed is small, but it grows fast. The maximal information in a volume is set by the surface enclosing it, and the inside can be described by degrees of freedom living on the boundary. The world becomes like a projection, where depth is encoded on a skin. The bulk is still real in experience, but it may not be fundamental in the accounting. The word holographic is not a claim that reality is an illusion, and it is not a retreat into metaphor. It is a claim about how information is organized in a quantum theory of gravity, where naive counting in the bulk overcounts what can exist. A hologram stores a three-dimensional image on a two-dimensional surface, and the depth is reconstructed from interference patterns. The black hole suggests nature stores a three-dimensional world on a two-dimensional boundary. The shock is not only about storage, because it reaches into what space is and how it could be built. If the fundamental degrees of freedom scale with area, then volume may be emergent, like a derived variable in a coarse-grained description. Space might be a reconstruction from entanglement patterns or other boundary data, an interior inferred from correlations. What we call inside may be a computed image, not the primary substrate. Gravity also starts to look different under this lens, and the change is both technical and philosophical. Black hole entropy ties geometry to information, and Hawking temperature ties geometry to quantum statistics, which is the mathematics of counting states. If geometry has thermodynamics, then geometry may have microstates, meaning it is not perfectly smooth at the deepest level. If geometry has microstates, then gravity may be collective behavior, like pressure emerging from molecular motion. That is the dangerous idea, because it reframes the earlier cracks in the cosmological model without introducing a single new particle. Webb's early galaxies strain our story of structure formation in a volume because they appear too massive, too early in cosmic time. The Hubble tension strains our story of distances through space because different methods disagree on the expansion rate. A drifting dark energy strains the idea that space-time is a fixed stage. Holography suggests the stage itself might be an effective approximation. In this framing, the universe is not primarily a three-dimensional container, even if it feels like one from the inside. It is an information system with a boundary rule, and the rule is enforced by gravity's ability to form horizons. The bulk physics we compute could be a coarse-grained description, like fluid equations that forget molecules. The forgotten details might live on a boundary we do not usually see. The phrase boundary does not have to mean a literal wall at the edge of the cosmos, and it is important not to picture a brick shell. It can mean a mathematical boundary in a space-time description, like a horizon, a causal boundary, or an asymptotic region. The principle is about where the degrees of freedom reside, not about a physical fence. The boundary is where the ledger is written, even if the boundary is only defined by light cones and infinity. This is where the documentary's mystery deepens, because it connects back to the central question with a new kind of suspicion. If Webb is revealing breaks where the model was confident, perhaps the confidence assumed volume-first reasoning at every step. Perhaps our cosmological bookkeeping is missing the boundary terms, the contributions that do not show up in a purely bulk description. Perhaps the universe is not failing our equations, because our equations are written in the wrong language. The black hole story also carries a second, darker paradox that cannot be ignored, because it threatens quantum theory itself. If black holes radiate thermally, then they can evaporate, and evaporation can proceed until the black hole is gone. If they evaporate completely, what happens to the information that fell in? Thermal radiation looks random, and random output suggests information loss. Information loss would violate quantum mechanics, at least in its standard unitary form, where the evolution of a closed system is reversible in principle. Quantum evolution preserves information, even when it scrambles it into correlations too complex to track. If black hole evaporation destroys information, then quantum theory breaks in a way that would echo across every field. If information escapes, then the horizon is not a one-way eraser, and the bookkeeping must be subtler. This tension became the black hole information problem, and it sharpened the need for holography as more than a poetic idea. A boundary description offers a way to keep unitarity while explaining thermal behavior, because the boundary can store correlations that the bulk seems to lose. It suggests that what looks lost in the bulk is encoded in fine-grained patterns on the boundary. The ledger is not burned because it is rewritten. You can feel the conceptual pressure building here, because each principle is non-negotiable in its own domain. The second law demands that entropy does not simply vanish from the exterior description. Quantum mechanics demands that information is not destroyed by time evolution. General relativity demands that horizons exist and that they behave as causal boundaries. The universe is forcing these demands into the same room, and the room is getting smaller. For the documentary's broader arc, the lesson is structural rather than merely technical. The universe forced a radical idea from a conservative demand, and that is the pattern we keep seeing. Preserve the second law, preserve quantum mechanics, and preserve gravity's geometry. The only way to keep all three may be to accept that space is not fundamental. Now return to the race. The marathon metaphor changes meaning when space becomes emergent, because a race assumes a track that exists independently of the runners. Mile markers assume a fixed track, measured in a stable geometry, and they assume that distance is a primitive quantity. If geometry is an emergent bookkeeping device, then the markers are part of the approximation. The pack at mile 5 might be an artifact of how we measure distance. That does not make the universe arbitrary, because holography is more constraining, not less, and constraints are what physics is made of. It says there is a maximum information capacity for regions, and that capacity is geometric, tied to area in Planck units. It says the universe has a hard limit on what can be stored and processed locally, even before engineering enters the story. Limits like that can shape what complex systems can do. A civilization is an information processing engine embedded in physics, and that framing is not metaphorical. It stores memory in matter, builds models in brains and machines, and coordinates action across distance and time through signals. If the universe enforces boundary limits on information, then there are ceilings on computation and communication, and those ceilings are not cultural. Those ceilings could become part of the Great Filter's physical substrate. The filter does not have to be a single catastrophe, and it does not have to be a dramatic cosmic event. It can be a universal scaling law that makes long-lived coordination exponentially hard as systems grow. If information is bounded by area, then expanding into volume does not buy unlimited capacity, at least not in the naive way. Growth might hit a geometric wall, even when energy seems abundant. This is not yet a claim about doom, because the chapter is building a conceptual tool rather than a prophecy. It is a reminder that survival is constrained by physics, not only by psychology, politics, or luck. If our cosmological model is cracking, the constraints might be stranger than we assumed, and the strange constraints may be the real story. The course might be harder because the track is not what we think. Holography also reframes fine-tuning from the previous chapter, and it does so without adding new knobs. If bulk parameters are emergent, then apparent independent dials might be linked by boundary consistency conditions, like compatibility requirements in a code. What looks like 26 locks could be fewer underlying constraints, because the boundary theory may allow only certain coherent bulk worlds. The corridor might be narrow because the ledger permits only certain balances. The next step is to make holography more than a suggestive principle, because physics advances by building explicit equivalences. It needs an explicit dictionary, not just a bound and a metaphor, and it needs a case where calculations can be matched on both sides. It needs a case where a gravitational theory in a volume is exactly the same as a non-gravitational quantum theory on a boundary. Without that, the idea remains a warning rather than a method. That transition arrives decades later, and it arrives with a name that becomes a landmark in theoretical physics. Juan Maldacena proposes a correspondence that makes holography concrete, and it does so with an audacious claim of exact equivalence. Gravity in a higher dimensional anti-de Sitter space is equivalent to a conformal field theory living on its boundary. The bulk and the boundary are two languages for the same physics. To visualize it, picture a deep space-time interior like a cavern, with geometry curving inward, and then picture its boundary as a bright, thin shell. On the shell, quantum fields fluctuate, interact, and compute. And in the interior, those same interactions appear as gravity and curved space-time. The correspondence says that nothing in the cavern is independent of the shell's bookkeeping. The interior is a translation, not an addition. The correspondence is not a proof that our universe is ADS, because our universe has positive cosmological constant behavior and an accelerating expansion. But it is a proof of concept that holography can be exact, not merely approximate or philosophical. It shows that space-time and gravity can emerge from quantum degrees of freedom without gravity in the boundary description. It shows that the boundary can be the real ledger. This is the climax beat for the chapter, because it turns shock into method and paradox into a working tool. The black hole entropy paradox forced area scaling, because the second law demanded a place to store lost entropy. Hawking radiation forced temperature and evaporation, because quantum fields refused to stay quiet near horizons. The information problem forced a boundary description, because unitarity demanded that nothing truly disappears. Maldacena shows a full dictionary where bulk gravity equals boundary quantum mechanics. The documentary's central question now has a sharper edge, because the earlier observational cracks can be read as hints rather than anomalies. If Webb is pushing us toward new physics, holography offers a candidate direction that is already disciplined by mathematics. It suggests that the failures of LCDM might be symptoms of treating emergent geometry as fundamental. It suggests that the universe we modeled with confidence could be a local projection. The horror in the title is not a monster hiding in space, and it is not a threat that comes from outside the cosmos. The horror is that space might not be the container we thought it was, and that our instincts about inside and outside might be reversed. The horror is that the deepest laws may live on a boundary, and our three-dimensional intuitions may be a convenient hallucination. If that is true, then our most confident extrapolations could be the least reliable. We end the chapter with the ledger balanced, but the bookkeeping rewritten, and that difference matters. Entropy is saved, yet the price is a new ontology, a new claim about what is primary in the world. Information scales with area, not volume, and the boundary may be the primary reality. The next chapter takes this from principle to consequence, and asks what Webb might be hinting at when the bulk story stops fitting. We have been treating space as the track and physics as the rules, because that framing feels stable under our feet. Webb keeps hinting the track itself is an approximation, smooth where we stand, but stitched together from something stranger. Chapter 5. Framed fine-tuning as 26 locks across scales, with no obvious master key hiding in the metal. Chapter 6 reframed the locks as bookkeeping, where horizons force information onto surfaces, and where inside becomes a story the outside can still tell. Now the narrative pressure shifts from principle to proof. In 1997, Juan Maldacena proposes ADS CFT, and holography stops being a slogan. The timing matters because the 1990s were a period of uneasy convergence. String theory, black hole thermodynamics, and quantum field theory were colliding without a shared language. The claim is blunt and unsettling because it refuses to stay philosophical. A gravity theory in a higher dimensional bulk is exactly equivalent to a quantum field theory without gravity on its boundary. It says that two seemingly different worlds, with different ingredients and different intuitions, can still be the same calculation. This is not an analogy, and it is not a heuristic picture that works only when nobody looks closely. It is a mathematical identity, with a dictionary matching quantities on both sides, and with consistency checks that punish sloppy thinking. On one side sits a curved spacetime called anti-de Sitter space, abbreviated ADs, drawn like a deep gravitational bowl. It has one extra spatial dimension compared to the boundary theory, and that extra direction behaves like a kind of depth that never quite ends. ADS is not just space with a sign flipped in a textbook equation. It has constant negative curvature, which means geodesics and light cones behave in distinctive ways, and signals can reflect off infinity as if the edge were a mirror. In the ADS bulk description, gravity is dynamical, and geometry can bend and ripple, responding to energy like a flexible fabric. Black holes exist as ordinary solutions, with horizons and temperatures, and their thermodynamics is not optional decoration, but a strict accounting of microstates. On the other side sits a conformal field theory, abbreviated CFT, which lives on the boundary and has no gravity in its fundamental equations. Conformal means it has no preferred length scale, so the physics looks similar under zooming, an abstract symmetry that becomes a practical lever. The correspondent says these are two descriptions of the same physics, even though they look like different genres of theory. Every observable in one language has a partner in the other language, and the partners line up in ways that can be computed, not merely asserted. Bulk fields correspond to boundary operators, and bulk geometry corresponds to patterns in the boundary state, like a shadow encoding a sculpture. The extra dimension behaves like a scale direction in the boundary theory, organizing which details matter at which energies. That last point is the first crack in intuition, because it turns distance into bookkeeping. Depth in the bulk maps to energy scale in the boundary, as if farther in means more coarse-grained, and near the edge means microscopically detailed. Visually, you can imagine a camera pulling back from a boundary surface covered in flickering quantum activity. As we move inward through the bulk, the flicker smooths into larger patterns, like pixels turning into shapes when you step away from a screen. ADS CFT operationalizes the holographic principle from black hole entropy, and it does so with hard equations. The boundary carries the degrees of freedom, and the bulk is a reconstruction, meaning the interior is not a separate storage device for information. In practice, the dictionary is concrete, and it has a specific hinge. The partition function of the boundary theory matches the gravitational path integral with boundary conditions fixed, so that sum over quantum histories is the same sum written in two dialects. Correlation functions on the boundary map to how bulk fields propagate through curved spacetime, including how disturbances spread and decay. entanglement in the boundary maps to geometric features in the bulk, suggesting that connectivity in space is built from connectivity in quantum information. This is where the correspondence becomes more than clever. When two boundary regions are strongly entangled, the bulk geometry between them tends to be smooth, while weak entanglement can look like thinning connections, as if space itself were losing structural support. The correspondence also explains why area laws keep appearing, even when our intuition expects volume. Boundary entanglement entropy is computed by a minimal surface in the bulk, and the surface area carries the count, like a soap film finding the least area shape. That statement has a precise form in the Ryu-Takayanagi formula, which ties entropy to geometry with a single, spare expression. It is striking because it makes a thermodynamic quantity, entropy, behave like a geometric object, and it does so without hand-waving. Now the narrative pressure shifts again, from what the correspondence says to why anyone trusts it. ADS-CFT has been tested in thousands of non-trivial calculations, and it survives because it keeps agreeing with itself in places where disagreement would be easy. The tests are not one dramatic prediction about our sky, because the correspondence is not built for our sky. They are consistency checks across thermodynamics, quantum chaos, and strongly coupled field theory, where ordinary perturbative tools usually fail. Black hole thermodynamics is a central verification channel, because black holes are where gravity and quantum statistics collide. A hot boundary state corresponds to a bulk black hole, and the entropy matches on both sides, scaling with area in the bulk and with degrees of freedom on the boundary. Even the temperature has a dual meaning that feels almost like a magic trick. On the boundary, it is ordinary thermal agitation in a quantum many-body system, while in the bulk, it is the surface gravity of a horizon, measured by how time warps near the edge. Transport properties provide another channel, and they are measured in the language of friction and flow, viscosity, diffusion and conductivity in the boundary theory, mapped to horizon dynamics in the bulk. So a black hole's response to perturbations becomes a fluid's response to stress. One famous result is the unusually low ratio of shear viscosity to entropy density predicted for certain strongly coupled plasmas. It is not that ADS-CFT explains every real fluid, but it shows that horizons behave like dissipative media with universal features. Even when exact calculations are hard, the correspondence gives controlled limits that scientists can actually use. Strong coupling on the boundary becomes classical gravity in the bulk, and computations become possible, because quantum fluctuations in the bulk are suppressed like noise fading in a large system. This is why ADS-CFT matters beyond elegance and beyond the aesthetic of symmetry. It turns quantum gravity into a calculational tool, by translating it into ordinary quantum field theory, where unitarity and locality are defined with familiar precision. It also matters because it answers the black hole information problem in a disciplined way, without relying on vague promises. If the boundary theory is unitary, then the bulk process must be unitary too, because the two are the same evolution described differently. Information cannot be destroyed in the bulk if it is preserved on the boundary, and that is not a moral claim. The horizon looks like an eraser only in the bulk language, while in the boundary language, it is a complicated scrambling device that still keeps the ledger balanced. Scrambling is an important word here, because it replaces the fantasy of disappearance with the reality of dispersal. A message thrown into a black hole is not annihilated, but mixed into correlations so thoroughly that only an absurdly precise decoding could retrieve it. Now return to the race. If gravity can be rewritten away in a boundary description, then gravity may not be fundamental, and that possibility changes the emotional temperature of every cosmological anomaly. Temperature is not fundamental, and pressure is not fundamental, even though they dominate our daily experience. They emerge from many microscopic degrees of freedom, and they disappear when you zoom in, because the molecules do not carry temperature as a primitive label. ADS-CFT suggests space-time and gravity could be like that, and the comparison is more than poetic. Geometry becomes a macroscopic bookkeeping device for underlying quantum information, summarizing vast entanglement patterns in a compact, smooth language. In this view, the bulk equations of gravity resemble hydrodynamics, which is powerful but not ultimate. They are effective equations describing collective behavior, not the deepest constituents, and they can fail when the underlying microstructure becomes visible. That reframes the fine-tuning corridor from Chapter 5, because the dials may not be independent at the deepest level. The 26 locks might not be separate knobs at all, because emergent variables can look separately adjustable even when hidden constraints bind them together. A deeper theory can enforce constraints that only appear as coincidences in the emergent description, which is why fine-tuning can be a symptom. When we choose the wrong variables, we can mistake a derived relationship for an unlikely accident. This does not automatically pick chance, necessity, or selection as the final answer, and it does not let us stop thinking. It changes the question by asking which parameters are fundamental enough to be tuned, and which are merely coordinates on a higher level map. If space-time is emergent, then some apparent tunings could dissolve into consistency conditions, like angles in a triangle forced by geometry. Others could remain as real selection effects in the underlying theory, meaning the deeper layer still has its own landscape of possibilities. Now the narrative pressure shifts toward humility, because ADS-CFT has a sharp limitation that can't be politely ignored. Our universe is not exactly anti-dar sitter, and the mismatch is not a small technicality. ADS has negative cosmological constant and a time-like boundary at infinity, which makes the boundary theory cleanly defined. Our universe looks closer to de Sitter, with positive dark energy and accelerated expansion, and with horizons that behave differently from ADS's reflective edge. In de Sitter space, the boundary is less like a laboratory wall and more like a horizon that limits what any observer can access. That difference complicates the holographic story, because the neat place to store the degrees of freedom is harder to identify. So the correspondence is not a direct model of our cosmos, and it is not a plug-in replacement for LCDM. It is a proof that holography can be exact, and that gravity can emerge from non-gravitational degrees, which is already a profound shift in what we consider plausible. That proof changes what we should consider plausible, and it tightens the range of respectable speculation. It says the idea is not metaphysics, because it can be written as equations and checked, and because the checks are hard enough to be meaningful. Now connect this back to Webb and the cracks in LCDM, because the telescope is forcing theory to show its seams. LCDM has been our bulk description, and it has worked astonishingly well locally, like a map that is perfect for a city but uncertain at the continent's edge. It fits the CMB power spectrum, large-scale structure, and many distance measures, and those successes are real. It also assumes space-time geometry is fundamental and smoothly defined everywhere, so that extrapolating backward is mostly a matter of evolving the same stage to earlier times. Webb's early galaxies strain the growth timeline under that assumption, because massive, organized structures appear when the model expects youth and disorder. The Hubble tension strains the distance ladder under that assumption, because different ways of measuring expansion refuse to converge on one number. Desai's hints of drifting dark energy strain the assumption that late-time acceleration is a simple constant, and the strain shows up statistically before it becomes a headline. Each anomaly is a stress test of the bulk story, probing whether our smooth geometry is a faithful foundation or a useful approximation. If space-time is emergent, then LCDM may be an effective theory, and effective theories have a characteristic failure mode. They can be accurate in a domain, then fail when extrapolated too far, because the coarse-grained variables stop tracking the true degrees of freedom. That is not a loophole that explains everything, and it is not an excuse to treat anomalies as free passes. It is a warning about overconfidence when we push a local fit into a global ontology, turning a successful model into a claim about what reality must be. Webb is pushing us into regimes we used to treat as clean, and it does so with images that feel almost accusatory. It looks back toward the first few 100 million years, where small modeling errors compound, and where our priors about star formation, feedback, and dust can quietly bias our reconstructions. If the bulk geometry is a reconstruction from deeper information rules, then early universe inference could be missing boundary terms, or misweighting correlations that matter at high energies. The mismatch could look like impossible galaxies, when the deeper accounting would call them natural outcomes of different bookkeeping. If distances and expansion are emergent bookkeeping, then different rulers can disagree without a single, simple systematic, because they may be sensitive to different coarse-grained variables. The mismatch could look like the Hubble tension, while the deeper description would say both measurements are locally correct in their own operational sense. If dark energy is not a constant, but an emergent effective parameter, then drift is not surprising, and the surprise becomes a clue. It becomes a symptom of using the wrong coarse-grained variable, like treating a changing medium as if it had a fixed refractive index. Now the narrative pressure shifts from explanation to consequence, because emergent gravity is not just a technical relabeling. If gravity is emergent, then the universe has an edge of the map, a place where the bulk language stops being the most fundamental description. The edge is not a physical wall in space, and it is not a barrier a spaceship could crash into. It is the boundary of a description, where the bulk language stops being fundamental, and where the true degrees of freedom live in a different accounting system. When we cross that boundary, familiar intuitions fail, and the failure is not gentle. Space stops being the container and becomes the output of a deeper accounting system, where is derived from patterns of correlation rather than assumed as a backdrop. That is the horrible discovery hinted by Webb, and the horror is conceptual rather than cinematic. It is not a monster hidden in the dark between galaxies, waiting for a spotlight to reveal teeth. It is the realization that the arena itself may not be what we thought, and that our confidence could be parochial. The track can be locally flat and globally misleading, like a road that seems straight until the fog lifts and the cliff appears. Now return to the marathon metaphor one last time, because metaphors are how we carry abstractions without dropping them. A crowded pack at mile 5 is not reassurance if the course has a universal breaking point, and if the decisive gradient is hidden beyond the next bend. The more runners we see early, the more likely the decisive filter is ahead, because early abundance removes early scarcity as the explanation. Webb's abundant early structure and abundant habitable worlds sharpen that logic, making the silence harder to dismiss as a simple lack of starting material. If physics has a boundary, then civilizations may face boundary-like limits too, even if they never learn the equations. Information, energy flow, and coordination scale in ways that can impose hard ceilings. And those ceilings can be invisible until a system approaches them. A civilization is a computation embedded in matter and constrained by geometry, and that is a plain statement with sharp edges. If geometry is emergent, then the constraints may be deeper than engineering, because the limits may come from the information-theoretic substrate rather than from the visible bulk stage. The Great Filter might not be a single disaster, and it might not be an asteroid-shaped answer that lets us point to one cause. It could be a near-universal scaling failure that appears only after a threshold of complexity, when coordination costs, heat dissipation, and fragility rise faster than capability. That is why the silence stays disturbing, even as planets multiply, and even as our catalogues fill with candidates. The pack can be dense because the cliff is later, and cliffs do not announce themselves, especially when the runners are still breathing easily. Now the final turn. The telescope built to reveal the past becomes a warning about the future, because it reveals how much of our confidence rests on the assumed nature of the arena. Webb is not only showing early galaxies, and it is not only refining parameters by a few percent. It is showing that our confidence about the arena may be local, and local confidence can be the most dangerous kind, because it feels like certainty while it is still untested. If ADS-CFT is a clue to a deeper principle, then space and gravity are emergent, and our cosmological model is a patch on a larger rulebook. If that is true, then Webb's anomalies are not noise at the margins, but the first hints we have pushed the model past its domain. We end where we began, at mile 5, with a full field, hearing the footfalls and feeling the crowd's momentum. Being surrounded at mile 5 is not comfort, because it means the filter is still ahead, and because the course itself may be the thing that decides. And if physics has a boundary, so might civilizations, whether or not they ever name it. The boundary does not care how hopeful the runners feel, because it is written into the course, and the course does not negotiate. We started at mile 5, surrounded by habitable worlds and early starlight, and noticed how comfort can hide the real attrition. Webb's deep fields then pushed that unease into numbers, with galaxies that seemed too bright too early, forcing us to interrogate every rung of the inference ladder. From there, the cracks lined up into a pattern. The Hubble tensions split our cosmic rulers. Deci hinted the acceleration itself may drift, and fine-tuning began to feel less like elegance and more like a locked room. That locked room led us to an older, stranger accounting system, where black holes keep their entropy on horizons, and what exists is limited by what can be stored. Bekenstein and Hawking turned gravity into bookkeeping, and holography suggested the ledger might live on a boundary, not inside the volume we inhabit. Maldaceno's ADS-CFT didn't give us our universe, but it proved a possibility that is hard to unsee, that space-time can be emergent, stitched from entanglement, with gravity behaving like a thermodynamic response rather than a fundamental force. And that possibility loops back to every earlier anomaly with unsettling efficiency. If LCDM is a bulk approximation, then Webb's early galaxies, the mismatched expansion rate, and a drifting dark energy are not random glitches, but symptoms of using local rules beyond their jurisdiction. Yet the story stays honest at the edge, because dust, feedback, lensing, and selection effects can still masquerade as revolution, and spectroscopy and cross-surveys will decide which discomforts survive contact with better data. The 26 locks are where the mystery sharpens, because they may be independent dials, or they may be a single constraint seen through a broken coordinate system. If the universe's true degrees of freedom live on boundaries, then what looks like tuning in the bulk could be bookkeeping on the edge. With constants and initial conditions emerging from information limits we haven't learned to write down. That reframes the 3 responses we offered: chance, necessity, and selection. Not as philosophies, but as competing predictions about what future measurements should reveal. Chance would look like a multiverse-like scatter, with no deeper correlations, and the locks staying stubbornly independent as our precision improves. Necessity would look like hidden relations, attractors, or dualities, where changing one constant forces, compensating changes elsewhere, reducing the apparent freedom of the dials. Selection would look like a statistical signature, not just "we are here," but distributions of parameters across cosmic history that cluster near habitability thresholds more often than blind dynamics would suggest. Most importantly, each path implies a different kind of test, and those tests are already being assembled. Webb's spectra can confirm or demote the impossible galaxies and map early metal and dust budgets, while DESI and its successors can check whether the drift in dark energy persists across redshift and probes. And if emergent gravity is more than metaphor, it should leave fingerprints in how structure grows, how horizons encode entropy, and how cosmological parameters correlate when we stop treating space-time as the primary stage. There is also the unresolved, almost poetic obstacle we can't ignore, because it is exactly our universe's shape. AD-SRC-ZFT works cleanly where there is a time-like boundary, but we seem to live in something closer to de Sitter space, with horizons and no obvious place to pin the ledger. Extending holography to de Sitter is not a solved problem, and that gap matters, because it is the difference between a beautiful analogy and a new foundation. Still, the documentary's through line is not that Webb proved a new cosmos, but that it forced a reckoning with where confidence comes from. The same model that predicts the microwave background with exquisite accuracy may fail when asked to explain the first heavy galaxies, the present expansion rate, and the detailed history of acceleration. That is not a scandal. It is a sign that we may be nearing the boundary of an effective description, where the map is accurate in the city and misleading at the coast. In that light, Webb's strangest gift may be humility, because humility is what lets us treat anomalies as data rather than embarrassment. It is what keeps the great filter question from collapsing into either despair or complacency. And it is what makes the next decade of cosmology feel less like cleanup and more like exploration. The universe may not be lying exactly, but it may be speaking a dialect our equations only approximate, and it gets louder the farther back we look, and the great filter metaphor returns, now with a sharper edge. If our physics is only locally true, then our Mile 5 crowding could be a mirage created by incomplete rules. And the real bottleneck may be tied to information, entropy, and horizons. A civilization can master chemistry and energy, yet still crash into scaling limits imposed by the universe's ledger. Limits that don't care about intelligence, only about what can be stored, cooled, coordinated, and preserved. So the central question changes shape, without losing its teeth. If Webb is revealing that our most confident model breaks where it should be strongest, then the implication is not merely that we need new parameters, but that space and gravity may be emergent, and the course may be designed by boundary rules we barely understand. In that universe, survival is not only about building rockets or avoiding wars. It is about learning the true constraints of reality before we run out of time to adapt. That brings us back to the opening image, the marathon where too many runners appear at the finish line. Maybe the crowd at Mile 5 does not mean the race is easy. It means the hard part has not started, and our instruments have finally reached the first hill. Webb did not show us monsters in the dark. It showed us that the dark has structure, and that structure may be the only honest guide to what comes next. If there is closure here, it is the kind that closes a chapter, not a mystery. We can now name the fault lines, early galaxies that stress growth, rulers that disagree, acceleration that may not be constant, constants that feel too carefully set, and horizons that insist information lives on edges. We can also name the wager that the universe we modeled with confidence is a local approximation, and the deeper reality may be written on a boundary we have not yet learned to read. And if that is true, then our optimism is not wrong. It is simply early. The most dangerous moment for a civilization may be when it feels cosmically ordinary, because that is when it stops asking what the universe is really charging for existence. The mile markers ahead may not be made of distance at all, but of entropy,